How's everybody doing? Have a good weekend. Hopefully the homework didn't take up too much of the weekend. Um, Hopefully the homework's going okay. If you didn't catch it, on Friday we had the help session. I recorded the help session. That's posted on Google Classroom with all of our other recordings. Um, there, I kind of went through the homework and I talked about each problem and I kind of explained in general how to approach it. So if you are still working on the problem and you were struggling on any individual questions, taking a look at that recording and finding the part where I'm talking about the homework would probably be helpful. Um, and yeah, just a friendly reminder that homework is due tonight at midnight. Canvas should be set up so that you can submit it there. It does require that you submit it as a PDF. So making sure that you have some way to scan, if it's like a physical homework that you're scanning it and turning it in as a PDF, that's going to be the only file it will accept. So just make sure that you are um, if there's any concerns with how to do that, let me know, but make sure that converting to like a PDF doesn't prevent you from submitting. Um, good morning. Howdy.
Howdy.
Thank you all so much for being here today. We are going to start with our first quiz. So what I'd like y'all to do is kind of clear your desks of paper. Basically, the only thing you're going to need is a pencil and or a pen, maybe an eraser. So yeah, if y'all wouldn't mind clearing your desks of anything that's not a pencil, that would be awesome. And yeah, I guess I'll go ahead and start passing this. Don't look at it until I tell you to. Please. Please don't take a look at it until the time starts. Alrighty, y'all are good to flip it over and begin. You're gonna have 5 minutes. I'll set a timer up front. If you have any questions about what it's asking, let me know. And when you're done, you can bring it up to me. No, the example is just so you see the format of what the answers are supposed to look like. I added 30 extra seconds, so you got about one more minute. Alrighty, that is the end of time. If y'all would please put your pencils down and pass those forward. Make sure your name is on it. Got everybody? All right. That was our first quiz. So hopefully it went okay. Um, the way that I am gonna do the quizzes is that so I was saying that we're gonna have one about daily. I didn't give one in the first week because it was the first week. So this quiz is giving you a good idea about like when we're thinking about the kinds of questions we might be asked. Um, Generally, there's more like concept and like those styles of like in the homework you have the questions and then you have the problems. So the questions are more like conceptual, making sure we understand fundamentals about the units, what these quantities mean, like what the physical meanings are. And so as we're going through our class and I'm introducing new quantities, I think it's really important that we know the units of the quantities that we're working with and that we know like physically what they represent, because otherwise you're just looking at them as like abstract mathematical symbols and you're losing the physics, which I think it's good if we understand both. So I'm going to try to get us to practice that kind of thinking. I try to do that in the lecture. I try to do that in the homeworks. That was the first quiz, right? So if the quiz didn't go well, we have it's the first one, right? So this is the first one you're seeing. Hopefully the time didn't. Oh yeah. So just in general, right? Class starts at 10, and we're going to be doing our quizzes in the first 5 to 10 minutes of class. So it's super important that we're in class, that we're here on time, because that's basically the time to expect. Two quizzes get dropped, right? So if a quiz didn't go well, you'll be able to, one or two bad quizzes isn't going to punish you. Also remember that we have a grading kind of scale that will be adjusted based on the weights that are going to help your overall grade the most. So if you look in the syllabus, the quizzes can be anywhere from 10 to 20%. So if we have a bad quiz, don't panic. Use it as a learning opportunity. Use it as a time to reflect and make sure as we're going through the class that we're thinking about these kinds of things. I'm big on concepts. I'm big on definitions and the physical meanings of these quantities. Um, so hopefully that all makes sense. I think you'll find that if you go through the first two lectures, you'll see the answers to those quiz questions, and I'll try to grade them as soon as I can. On Canvas, I will post the old quiz and I'll post your grade, so that if you want to go back, you'll be able to know what quizzes there were, and I'll grade these and I'll try to pass them back by next class. Thank y'all for indulging in that quiz, and let us move forward. So today we are going to be talking about solutions to the one group diffusion equation. Um, Last class, we derived this equation on the board. This is the one speed or the one group neutron diffusion equation. So in terms of like thinking about physical significance of the terms in that equation, every term, this term, this term, this term and that term have have physically meaningful units. It's a reaction rate density, or it's a yeah, it's a physically meaningful rate density. So if you look at the units of all of these terms, they're going to have units that look like neutrons per unit volume and per unit time. So if we know the units of each of these individual symbols, then we can make sure that we can check and see that all of the units of each of these overall terms match up. Um, to solve this equation, it's a partial differential equation. It's got a time derivative. The Laplacian square, that this little triangle, the square is the Laplacian, basically means you're taking a second derivative with respect to space. So to solve this equation, you need initial conditions, you need boundary conditions. The flux itself is a continuous function, so you have a continuity condition, and then the flux also, if we think about the definition of flux as like a path length rate per unit volume, then as a path length, it can't be negative, right? You can't have a negative path length, and you can't have an imaginary path length. You also can't have an infinite path length. So the scalar flux has physical conditions that make sure that the flux is always positive and doesn't blow up to infinity. So this is the equation that we derived. It is an approximation because we did that Fick's law substitution for the current density. That's how we got this net leakage rate density term. So it's not exact, but it is relatively accurate, especially if you have a large reactor. So this equation, even though it's not exact, is very useful to understand how neutrons distribute themselves spatially in a reactor. And that's what we're going to talk about today. We're going to look at this equation. We're going to attempt to solve it. And in solving it, we're going to see how it evolves with time. And we're going to see some steady state solutions to the equation. And in doing that, we'll learn how to predict what the flux is in like a bare critical reactor of a simple geometry, like a cube or a sphere or a cylinder. And in doing that, we're also going to understand multiplication and criticality on a deeper level. So anytime you write the one group diffusion equation, it has approximations that are built into it. We want to know about what those approximations and assumptions are so that we don't mistakenly think that we can apply this equation to any problem. So we're already assuming that it's homogeneous. The reactor is made of like one material and it's bare, which means that it's like surrounded by a vacuum. Inside of a vacuum, what do y'all think the neutron flux is? Zero, right? Vacuum means absence of all particles. So in a vacuum, you have no neutrons, therefore you have no neutron flux. So there's some flux distribution in our reactor, but once you get outside of its boundaries and you have vacuum, then the flux goes to zero. We're assuming that all of our cross sections are constant, or at least they have weak dependence on position. That's why in this equation, I'm not writing any arguments on nu F, on sigma F, on sigma A, or on the diffusion coefficient. All of those are material properties, but if we're assuming that our reactor is homogeneous and these cross sections don't change with space, then I don't need any arguments inside of the scalar flux to say it depends on position or it depends on energy. And we can ignore the energy dependence because of what we're assuming about these cross sections being averaged over over all of the neutrons in our reactor. We're also assuming one group, and that assumption is important. It means that, like, in a real reactor, we have a distribution of energies. In the one group diffusion equation, it's like we're averaging all of those energies so that we're assuming that all of the neutron populations have like a average kinetic energy and an average velocity. So diffusion theory assumes that there's no absorbers, or at least that if there are absorbers, they are weak absorbers. So like if you're trying to apply diffusion theory in a control rod of a nuclear reactor in the real world, diffusion theory would be bad at the control rod because the control rod is an absorber. All of the dimensions need to be greater than the neutron mean free path. That basically allows for the neutrons to diffuse through the medium. If the dimensions of your reactor are very, very small, then neutrons don't even have reactions in that little space if the dimensions are less than the mean free path. So the reactor has to be big so that the neutrons can diffuse through the medium. Thinking about diffusion, thinking about like the pizza box analogy, where it's like if we put a pizza in the corner of the room, the pizza particles will diffuse through the room, and sometime later people in the back of the room will smell the pizza because those individual like pizza particles are escaping the box, they're diffusing through the room, eventually they're getting to you, they're getting inside of your nose, and then when you smell it, it's because those pizza particles have diffused all the way into your nose. So the neutrons, we're picturing them as kind of doing the same thing. um, and we're assuming that the nuclei are at rest, which is why there's no arguments on our cross section. um, we're assuming that there's not very much scattering, and if there is scattering, it's all isotropic. And if all of those conditions are met, that means that Fick's law is valid, and then we can use one group diffusion theory. So these are like the conditions, these are the assumptions and the limitations of diffusion theory that we should be aware of. So like we were saying, we're ignoring energy dependence by just assuming everything has been averaged, the energies have been averaged, and therefore we have like a characteristic energy and velocity. So this is the same exact equation. The only thing I'm doing is I'm spelling out the arguments on the scalar flux, that this is a partial differential equation. We have a time derivative. We have effectively space derivatives. So our flux depends on the position in the reactor, and it depends on time. Oops. Sorry, I'm sharing the wrong thing, and I wanted us to fill these out together. Sorry about that. One moment. Let me actually pull up their right slides. Okay. Apologies. So whenever we have this equation, we want to know about the conditions that we have to apply to attempt to solve this equation. When we talk about the vacuum boundary condition, that is telling us that at our boundary, so our flux at this external surface, and at all times t, we have a vacuum boundary. So our ext is the extrapolated dimensions of the reactor. The reactor, like if it's a cylinder or if it's a sphere, it would have a radius. The extrapolated radius is an extra distance that we add to the dimensions so that we can say at that extrapolated distance, the flux goes to zero. So if we have a vacuum, we already said the flux is zero there, and that is how we would write our vacuum boundary condition. We're saying the flux at our extrapolated boundary and at all times t is equal to zero. Um, in terms of an initial condition, that needs to be telling our equation what's the shape of our flux at the starting time. So we're saying our flux, we need to know at for all positions and at time zero, we need to know the shape of the flux. So we can say phi0 of r is the shape of the flux at the initial time. So boundary conditions say what the flux is at the boundary. The initial condition says this is what my scalar flux looks like at the starting time. Um, in a real reactor, you have multiple materials. So at an interface from one material to another, you might have interface conditions. We're dealing with a one-region reactor right now, so we'll ignore interface conditions for now. Um, continuity is that this flux, this scalar flux function has to be continuous. So it has to be continuous within the reactor volume. That means it's a smooth function, right? That means that it can't have any like weird discontinuities or breaks in the function. And then this scalar flux, it's like a path length rate per unit volume. Path lengths can't be negative. Path lengths can't be imaginary. Path lengths can't be infinite. So this scalar flux has to be bounded between 0, this function phi, which is a function of position and time, has to be bounded between 0. It can be equal to 0, but it can't be negative. And it can be very, very large, but it can't be infinitely large. So these are the conditions that we're talking about when we say we've got these various conditions that we have to apply to our reactor to solve this equation. These are what those conditions look like for a bare homogeneous reactor. And in general, none of these will really change except for the boundary conditions when you have different problems. But and when you have multi-region problems, you'll have interface conditions. So this is like the mathematical setup for our problem. And then once we have this, and also once we know the geometry, the Laplacian is going to change based on what your geometry is. So once you know this, and you know your geometry, and you know your Laplacian, you basically have everything that you need to begin to solve the problem. So just as a little kind of review of these operators, because in last class we wrote Fick's law, which is based on the gradient of the flux. We used Gauss divergence theorem to rewrite J in terms of a volume integral. We converted the surface integral into a volume integral, and in doing so, we ended up getting divergence out of there. And then um, if you take the divergence of the gradient, that gives you the Laplacian, and that's what we ended up doing. So basically, these are operators. Just like the derivative is an operator on a function and it tells you you're doing the specific operation, these are all just operators. They have a meaning when they're next to a function and they're saying you do something to the function. So this table is a good one because it's telling you in each coordinate system what these operators look like. So when you do this gradient operator, the gradient always acts on a scalar function like the scalar flux. And notice that this gradient output has e hat x, e hat y, and e hat z for like 3D Cartesian. That means it's taking that scalar function and it's converting it into a vector. So it takes a scalar and it outputs a vector. Like if you're in Cartesian coordinates, it's saying you're taking the x component of your function, taking its derivative with respect to that component, and multiplying it by the unit vector in the x direction. And then in the y direction, you're taking the derivative of your function with respect to y and multiplying by the y unit vector. And you're taking the derivative of your function with respect to z and multiplying that by the z component. So generally, those are what those operators look like depending on what coordinate system you're in. The divergence is very similar, but it acts on a vector like J, the net current density, and it is going to return a scalar. So the divergence operator gives you a scalar. And notice these basically do effectively the same thing. It's just one outputs a vector and one outputs a scalar. It always means you're taking partials with respect to your function. It just depends on if it's gradient or divergence, if your result becomes a vector or if it becomes a scalar. And then Laplacian operates on a scalar and it returns a scalar. So in our equation, in our one group diffusion equation, we have the Laplacian of phi. One group diffusion equation is a scalar equation. All of those reaction rates are scalars. So the Laplacian of phi better also give me a scalar, because if I look back at this equation, all of the units of every term have to be the same, but also if this is a scalar and this is a scalar, and everything has to be either a scalar or a vector, right? So that Laplacian squared gives me a scalar, which is good. Generally, it's good to know what these operators are. This table is here so if you're doing your homework or if you, it's a good table to be aware of. And I think if I was going to give you, if we had an exam, there would be a formula sheet, and the formula sheet would probably have this information, but it wouldn't tell you what coordinate system it applies to. So we need to be familiar enough with these operators that we can recognize the form of each one. But I won't make you like literally memorize all of the operators, if that makes sense. So hopefully that's okay. This is a good table to be aware of for what we're going to be doing today. And so this is just explaining more about what I was saying about that extrapolated boundary. So if you have a vacuum, then the flux needs to go to zero in that vacuum. The extrapolated boundary condition is like an approximation that we make our integration easier. Because if we say that the flux goes to zero at this distance outside of the extrapolated boundary, we can just carry our integrals through that extrapolated boundary, and it makes all of the math way easier. So this picture right here is like showing this is inside of the reactor. This is the scalar flux in the reactor as a function of position. And this dashed line is like the surface of the outer surface of the reactor. So this distance right here, that's our S. That's the position of our surface, right? If you go from the origin all the way to RS, you get to the position on the outer surface. And E hat n is the unit normal to the surface. So this is your E hat n pointing outward on the surface. And this little distance right here, if we are extrapolating with the curvature of our solution, notice that this first curve extrapolates with the solution curvature. This little distance we call d. And that's the extrapolating distance. So one way we can extrapolate is by following the solution curvature. That's what that first function is doing. We follow the solution curvature, right? This is the flux inside of our reactor. This is the flux at the surface. And if we follow that function at one distance d over to the right, that is where our function goes to zero at that extrapolated distance. The other way we can extrapolate is by just following the slope of the scalar flux until we linearly hit this point right here. And so if we use a linear extrapolation distance, that's what this is. D linear is if you just extrapolate with a line that follows the flux slope at the surface. Um, And if you look into like neutron transport theory is really where like the detailed like heavy math with nuclear engineering really comes from. From transport theory, they tell us what the good diffusion or what the good extrapolation distance to use is. And so for the linear extrapolation distance or the curvature extrapolation distance, we can both approximate these pretty well with 2 times the diffusion coefficient. That's one of those things where we can just we're good to just say it comes from transport. And if you need to know what that distance is, that extrapolation distance, we're pretty much always going to use 2D. Just it's important to just mention that this is 2D in the direction where you're extrapolating. So like if you have a radius, you would add 1 extrapolation distance. But if you had a cylinder that has a certain height, then you would need an extrapolation distance on the top and the extrapolation distance on the bottom. So the overall extrapolated distance would be the height plus 4 of the 4D, because you're going 2 up and 2 down, whereas the radius, you just go 1 out in every direction. And the other boundary condition that we can talk about for vacuum boundary conditions is called the Marshak condition. And basically what we're doing is just we're going from this point right here. So we're looking at the flux at the outer surface. And we're saying if I follow that slope to this point, going a distance of 2d to the right, I will end up at 0. So if I take this value plus the distance that I'm going to the right times the slope in that the slope of my function, which we can represent as the gradient of the flux at the outer surface, dotted with our unit normal, that quantity gives us 0. This is saying this is the value of my function at Rs. This is the distance that I'm going to the right, and this right here is the slope of my function. So if I follow that slope, if I follow the solution slope to 0, that's basically what I am doing. And it leads to this Marshak boundary condition. So when we were talking about different kinds of boundary conditions, we were saying there's like the boundary condition where you specify the value of your variable. That's like the vacuum boundary condition where we're saying the value of our variable is 0. This is like a mixed boundary condition because we're saying at the boundary, the equation depends on both the value of my function and the derivative of my function. So that's like a mixed boundary condition because it depends on the value of the function and the function's derivative. So that's everything we need to know about this extrapolated boundary and where that comes from. Um, in this picture, the D and the D linear are being greatly exaggerated. So it is okay if we approximate them with the same value of 2 times the diffusion coefficient. Um, and yeah, so that's the extrapolated boundary. We had already talked about multiplication factor. We talked about it as the rate of production in our system over losses of our system. If you're looking at a like the fission rates in a nuclear reactor in the fission process, some instant neutron causes a fission. That fission event releases neutrons. Some of those neutrons, like this one right here, will go on to make a new fission reaction and will continue the chain. Some of these neutrons, though, will hit a nucleus that won't cause a fission, but will just be like absorbed and not continue the chain reaction. Ideally, in our reactor, every fission causes one new fission so that our reaction rates don't like blow up exponentially. Because if one neutron if 2 neutrons cause 2 fissions, and then those resulting 4 neutrons cause 4 fissions, and then those 8 neutrons cause, you can see how this blows up exponentially if you don't have some of those neutrons being captured. So in our reactor, we have to have some absorbing material to make a configuration where production and loss are balanced. And depending on which is bigger, the production or the losses, we can talk about the configuration of our system as being critical or subcritical or supercritical. Basically, if the production is bigger than the losses, that means your population is going to increase exponentially, and that's what we call supercritical. If your production and your losses are balanced, that's what we call a critical configuration. And if your losses are greater than your production, then your neutron population is going to decrease with time, and that's what we call subcritical. These definitions are all based on what's happening with our reaction rates, ignoring any sources. So if you have a source, it doesn't change how we define K in terms of what it means to be supercritical or critical or subcritical. It just might change the behavior of the reactor. And that's what you would have seen in homework 1 when you had that problem where you looked at the infinite medium, but you add a source. And we'll talk more about the distinction between when do you think about the source and when don't you. But this is just a review of what we talked about last time. And we can kind of get a better understanding about criticality from this one group diffusion equation. And here we're writing it in the steady state form. So if I just go back real quick, if we want to look at this equation in steady state, how does it simplify the equation? Yeah, right. If it's steady, that means nothing is changing with time. So any d by dt of a quantity is going to be 0. Any time derivative is going to be 0. So if it's steady, this flux is not changing with time, so we can knock that out of the equation. And that's all that this is, right? It's that exact same equation. We've just made the time component go away because we're saying it's in steady state. Notice that on the left, this quantity right here, what does that represent in our equation? It's the net leakage. And what does this quantity represent? It's the absorption rate density, and this is the leakage rate density. So notice that these two quantities on the left, we can both think of those as losses. Sorry, it's just a loss. The left side is a loss rate. And then notice on the right-hand side, that's our fission production term, right? That's our production rate density. So the right-hand side is a production rate. The left side is representing our losses. The right side is representing production. So if we were to arbitrarily multiply the left side by some number, then we could talk about what that number means in terms of our criticality conditions. So if this number ends up being less than 1, what does that mean about our reactor in terms of the criticality condition? If this number is less than 1, does that mean that the reactor is critical or supercritical or subcritical? If this number that we're just saying I have some number and I'm multiplying it on the left-hand side. Um, and I want to ask the question, if this number ends up being less than 1, what does that mean about my reactor configuration in terms of like supercritical or subcritical or critical? Supercritical, right? Because if this number is less than 1, we can move the loss rate to the other side. So it says number equals production over loss. And if the number is less than 1, it means that your production, sorry, subcritical, right? It means that your production is less than your losses. So this is going to be subcritical. You could basically say that if this is my equation, then I have number equals production over loss. That's kind of like just rewriting the equation, basically. So if the number is less than 1, then it's subcritical. If the number is equal to 1, what does that mean? Critical, right? That means that my production and loss will be equal if k is 1, or if that number is 1. And then if that number is greater than 1, obviously we have supercritical, right? So this number, if we call it k, then what our equation looks like is negative d times the Laplacian of phi of r plus sigma a times phi of r equals 1 over k times nu f times sigma f times phi of r. So this is how we can write the diffusion equation as an eigenvalue equation, where this k, and really we can call it k effective. This k is the eigenvalue of the equation, and the flux is the eigenfunction. And when I write this equation, both k and the flux are unknowns. Um, if we want to solve this equation, we basically need a k and flux pair. And if we can make this equation satisfy our boundary conditions and our initial conditions, then the corresponding value of k and phi will be like physically meaningful. And we can go through an eigenvalue problem solving process to figure out what is my value for k effective and what does my corresponding flux shape look like. So that's kind of the goal that we want to be able to achieve. Also, when I wrote this equation, how come I'm not writing any time arguments on the scalar flux? It's steady state, right? When we're ignoring d by dt, it also means nothing is changing with time, so we're free to be lazy and ignore the time argument because nothing will be changing with time if it's steady state. So when we talk about these k eigenvalue problems, you might be wondering, can it have a time derivative or a time component? And the answer is no. These k eigenvalue problems are specifically looking at how does the solution evolve in steady state. So it looks for k and phi pairs in steady state. So you can really only do eigenvalue problems in steady state. You might also be wondering, what if we add a source? Can we still do these kinds of problems if we have a source? And that answer is also no, that these eigen problems look at how the system behaves in the absence of sources. So we can say eigen problems look at the behavior without driving sources. Eigenproblems look at the system's behavior without any driving sources. So that's partly why when we talk about K effective, it is defined by definition to be production over loss when you have no sources in your system. If you go back to that original equation, you can hopefully, what we can say is that there's a lot of K phi pairs that satisfy that. In fact, if you were to ask how many, the answer is that there's infinitely many. Infinitely many. If you look at that past equation, you can find literally an infinite number of Ks and phis that would satisfy the equation. But lucky for us, we don't have to do that stuff that we maybe did in linear algebra where you like actually find all of those solutions as like some series. Yes. Yes, pairs. Sorry if my handwriting is bad. Hopefully, yeah. If you ever have a question about what's written, feel free to let me know. I will not take it personally. But yeah, so we do not have to find them all. We can use the physical conditions of our problem to basically say that there's actually only going to be one function that meets our physical conditions. There's going to be only one eigenfunction that's positive throughout the domain. And when I say the domain, it's like the domain of our reactor. If the reactor has a certain radius, there's only going to be one function there's only going to be one eigenfunction that is always positive in that domain. That eigenfunction in nuclear engineering has a very, very special name, and it is called the fundamental mode. The fundamental mode describes the shape of our scalar flux when our reactor is critical. And so that fundamental mode eigenfunction is our phi solution. The corresponding value of K is the largest eigenvalue of this. Of all of the possible eigenvalues, the one that corresponds to the fundamental mode is the largest eigenvalue. And in nuclear engineering, we give that eigenvalue a special name too, and we call it K effective. So that's kind of like a way that we can think a little bit differently about what the K effective or what the multiplication factor is. We can think of it as the largest eigenvalue of that K eigenvalue diffusion equation that we wrote here. So with this rethinking of the multiplication factor, we can also talk a little bit more about the production and losses as we wrote them on the last slide. And we can actually talk about these losses and productions as being operators. So in this case, we can rewrite the left side as a loss operator, where L, I'm making it like a bold L, because this is a operator. And the form of that, this is basically just the left-hand side of that diffusion equation. So this is minus d times the Laplacian of phi plus sigma a times phi. So the loss operator is kind of like any other operator. It's some mathematical object that acts on a function. Based on the form of our diffusion equation, it tells us what that operator looks like. And in this case, it's saying we take minus d times the Laplacian of our function, and then we add sigma a times our function. And similarly, we could write our production operator, p phi, and that's just the right-hand side of our equation. So it's nu f sigma f times phi. So it's the right-hand side without the eigenvalue. So if we write the loss operator like this and the production operator like this, then our one group diffusion equation, right, this was the left side, this is the right side, and then we have that 1 over k as a multiple. So this is how you can write the one group diffusion equation as a k eigenvalue problem. And if you wanted to get k times phi by itself, then what we would do is multiply both sides by k. And then to get L out of the left side, we would multiply both sides by L inverse on the left of the function. Because this L and this P are like linear algebra operators. So the way that you would get the way that you would get K phi by itself is that you would multiply both sides by K and then take the L inverse of both sides. So this is going to look like L inverse times P of phi. So if we use this definition, then it just gives us another way that we can talk about the definition of the multiplication factor. That in this case, if we write it like this, it's the largest eigenvalue of this L inverse P operator. So it's the largest eigenvalue of the L inverse P operator. So this is how we can define K effective in terms of operators. And if we define it in terms of operators, this is an important point because what we want to hopefully recognize is that when we talk about K effective, it only describes operators. It only describes basically the materials and the size and like the geometry of our reactor. It doesn't have anything to do with the neutron population. So it's an important point about K that it's based on the operators, it's based on production and loss, so it's based on your materials, your geometry, and your shape. It doesn't have anything to do with the neutron population. That's also why adding a source doesn't affect how we define K effective. So that's just that's an operator definition that is good to know. So in terms of these operators, P and L, that's going to kind of determine if we have a steady state solution. The P and the L operators have to be equal for our solution to be steady. And if they're out of balance, then our solution is going to evolve with time. So if we want to tackle this PDE, we can actually approach trying to solve it. And the standard way that you could start approaching solving a PDE like this is by doing separation of variables. So our shape function, our function, the thing that we're trying to solve in this equation, it depends on position and it depends on time. And if we do separation of variables, what we're going to assume is that this function can be broken up into one part that only depends on space and another part that only depends on time. So I can say it looks like some r of r times some t of t, where r of r is the spatial shape function. So it's a function that only depends on position. And t of t, or big T of t, is the time evolution part. It's a function that only depends on time. So if we make this substitution, then we can massage our equation and get a new form. So if this is the value of my flux, if it looks like r of r times t of t, if I take the time derivative of that, if I do d by dt of r of r times t of t, right? That's what we have on the left side here is the time derivative of the flux. We're saying the flux is this shape function times this time function. How does this simplify if this r of r only depends on space and has no time dependence? You just pull it out, right? Because when you do this, I could be better with my notation. These are partial derivatives. And if you recall with partial derivatives, if I'm taking a partial with respect to time, I'm treating any other variables as constants. So that r of r is a shape, it only depends on position. It can be pulled out of my time derivative. So this is equivalent to saying r of r times d big T d little t. And I guess just to keep the arguments there, dt of t with respect, yeah, the derivative of time with respect to time, or the derivative of the time function with respect to time. So hopefully that's okay. And we can do something very similar with the Laplacian, that this is saying we're taking the Laplacian of R of R times T of T. And the Laplacian is like doing space derivatives. Like if we're in 1D, if we're in 1D Cartesian, then it's just second derivative with respect to x. So the Laplacian doesn't act on any time functions. So just like we could pull, in this case, we can pull the time function out of this derivative because it doesn't, the time function doesn't depend on space. So this is going to look like T of T times the Laplacian of R. So we're just kind of spelling out what these terms in my equation will look like when I make this substitution. And then if I do make that substitution, then this R of R times dt of dt is on the left. And then on the right, notice that this Laplacian squared term becomes t times the Laplacian of R. And on the right, I'm just replacing phi with its definition, which is R of R times T of T. And then the only other thing I've done is I've multiplied both sides by V to put this speed on the right-hand side. So hopefully you can see with those substitutions how we get here. Do we all see how we can plug these into this equation, multiply by T, and then get this expression? If it looks unclear after class, take the time to actually go through the steps. We should hopefully see that this is all okay. And so this is what we got, right? This is that end, what we had at the bottom of the last slide. And once we're here, we just need to do one more thing, which is that we're going to divide both sides by the shape, by our solution. We're going to divide it by R of R times T of T. So if I look at the left-hand side and I divide the left-hand side by R of R times T of T, what is the left-hand side going to look like? If I divide these, what's going to cancel? The R's are going to cancel, right? And so I'll have my time derivative, and because I'm dividing by this, I'll have 1 over big T in the denominator. So the left-hand side is going to look like bit 1 over big T of T times times d t, d t, d big T, d little t. And when I divide both sides by this quantity on the right, what's going to happen? What's going to cancel when I divide by both sides? Divide this by both sides on the right. The t's, right? Because I've got a t of t right here, and I've got a t of t right here. So the t's will divide away. And so on the right-hand side, I'll have, in the r, the shape function will end up in the denominator here. So I'll have v divided by R of R times this quantity, but just with the t term divided out. So I'm going to have d times the Laplacian squared of R plus this quantity nu f sigma f minus sigma a times R of R. Oh, and I'm being lazy. Let me include my arguments. So yeah, that's what we get if we divide both sides by the solution variable. And this, we only really did 2 steps. We did separation of variables, we plugged that in, then we divided both sides by the function. And this is actually a pretty interesting point in the problem, because notice that this left-hand side only depends on time, and this right-hand side only depends on position. So imagine that I knew what this time function was so that I could plug in values of t and get some number. Like I could plug in t equals 1, t equals 2, t equals 3 on the left-hand side. If I'm changing t on the left-hand side, is it going to change what I have on the right-hand side? No, right? Because the right-hand side doesn't depend on time. So as I'm changing t over here, t equals 1, t equals 2, t equals 3, the right-hand side is not changing. The right-hand side is constant. And that means that as I'm changing the left side, the right side isn't changing. That means the left side can't be changing either, can it? So the only way that this function makes sense is if both sides are equal to the same constant. And we call that constant minus lambda. Then we can break this equation up into two separate equations, one that only depends on space. This is the space component, and then one that depends on time, and that's the time component. So we took this partial differential equation, which had a function, the solution was a function of two variables, and we've broken this problem up into two ordinary differential equations that are individually a lot easier to solve. And that's generally the process that you'll go through when you do separation of variables. At least that's the ideal kind of thing that you end up with. One thing that's a function of one variable, one thing that's a function of a completely different variable that allows you to separate the equations by saying that they're both equal to the same constant. So that's where we're at. And now we can start solving those two equations separately. So we're going to look at the space function first. This, what we have right here, this is this equation that we had on the bottom. Oh, question. Yes. I'm gonna hide the ball for a minute if that's okay. Um, so yeah, so this equation that I have right here, I've just rearranged this space term. I've basically gotten that v times r, and I basically distributed everything into these other two terms. So I've basically done a couple algebra steps to get here, but I promise this is just rearranging that equation so that you have all of these other constants multiplied by the like r function that's by itself, and then I have the Laplacian of r here. So all of these things that are multiplying big R, these are just constants. So I can lump all of these constants together and just call this big thing b squared. If I do that, then the resulting equation is a special kind of equation called the Helmholtz equation, and it looks like this. So we have the Laplacian of R plus some positive constant squared. Sorry, this is Bn, not Bm. Bn times our shape function, and it is equal to 0. And I need to put an n here, and I need to put an n here. So the r subscript n is just reminding us that this is an eigenvalue equation. R is the eigenfunction. Bn squared is the eigenvalue, and there's an infinite number of these kinds of equations. I could write this for any value of n from 1 to infinity. So we have an infinite number of eigenfunctions that satisfy this equation. We have an infinite number of eigenvalues that satisfy the equation. And this shape function still has to obey the boundary conditions of our original scalar flux. So we were saying that we had that vacuum boundary condition. So this R of R has to satisfy that boundary condition that if we evaluate this shape function at the extrapolated dimensions of our reactor, it better be 0. So this confines or limits what eigenfunction can satisfy the equation because it has to be one where it's 0 at our extrapolated boundary. It has to also always be positive within the domain of our reactor. And these Rn of R, these are the spatial eigenfunctions. Spatial eigenfunctions. And then the Bn's are the eigenvalues. So we might be worried like, oh my gosh, there's an infinite number. How do I do this? But the thing that's nice for us is that there's only one of these that's going to correspond to the conditions of our problem. And also notice that because B can change, like we have a different B for every solution to this equation, that means we're going to have a different lambda for every solution too. So we can kind of say that this is Bn squared, and then this is lambda n. So any value of Bn that I have, there's going to be a corresponding value for lambda. But so each Bn corresponds to a set of lambda n's. But even though there's an infinite number of these, there's only one that's going to satisfy our conditions. N equals 1 is going to end up being the only eigenvalue whose eigenfunction is everywhere non-negative. So at n equals 1, that is our special shape function that we want to be, that's the special shape function that we're after. And this is the fundamental mode eigenfunction. This is the fundamental mode eigenfunction. This is the only eigenfunction that will satisfy our boundary conditions and our physical conditions. And the corresponding eigenvalue is Bn squared. So from there, if we know that n equals 1 corresponds to our eigenfunction, then we can also know that B1, when n equals 1, that's going to give us our eigenvalue. And we give this a special name. We're going to call it Bg squared. And this is our geometric buckle. The smallest, the eigenvalue that corresponds to our eigenfunction is called Bg squared, which is the geometric buckle. So we had that previous equation that related the Bn's to the lambda n's. This is that equation. I've just done some algebra to get the lambda by itself. If I then do a little bit more algebra to factor out the speed times the diffusion coefficient, and I rearrange, then I get an expression for lambda 1, the corresponding lambda eigenvalue, that looks like Bg squared minus this quantity right here. This is nu f, sigma f minus sigma a over d. And this right here, notice that nu, sigma, and the diffusion coefficient, these are all what kind of properties? They're material properties, right? D is like, we're approximating D as 1 over 3 sigma t for now. So D is also based on sigma, which is a material property. These are all material properties. So this Bm squared, we give it its name, and we call it the material buckle. It's called the material buckling because it only depends on material properties in our reactor. Bg squared is the geometric buckling. As the name implies, it tells you about the geometric properties of your reactor. Crap. Okay, so I had originally just gonna. So I was originally. I got ahead of myself one sec. So this is actually where I wanted to say material buckling. My apologies. I was getting ahead of myself and not sticking to how I set things up on my notes. So that is this Bm squared. Apologies. And what I wanted to do here is kind of talk about this equation in a slightly, I wanted to massage this equation to see what we could do with it. So apologies for the change. What I wanted to do with this equation is I wanted to divide top and bottom by sigma a. So if I do that, I'm going to have nu f, sigma f over sigma a on this term. If I divide this by sigma a, I'm going to get a 1, right? And then in the denominator, I'm going to have d over sigma a. Hopefully that's okay. I'm allowed to divide both sides by the same thing. So I'm dividing top and bottom by sigma a. This quantity right here, nu f, sigma f over sigma a, do we recognize that from any fundamental definitions? That's k infinity specifically, right? So we can call this k infinity minus 1. This is like production over loss for an infinite medium where you have no leakage. So that's the definition of K infinity. And then this D over sigma A, we're going to call that L squared. So we're introducing a new thing, L, and L is defined as being the square root of D over sigma A. And we call this the diffusion length. L is the diffusion length. The diffusion coefficient doesn't really have physical significance, but L does. L is a length, and it tells you on average how far neutrons will diffuse in our reactor before they get absorbed by something. So if we think about the units real quick, what are the units of D? So remember D, the diffusion coefficient is 1 over sigma transport. So what are the units of sigma of a macroscopic cross section? It's inverse centimeters. And so if I've got inverse centimeters in the denominator, that means that I've just got regular centimeters for the units of D. So D has units of centimeters. And then I'm dividing by the units of sigma A. And what are the units of sigma A? Inverse centimeters. So I've got centimeters over centimeter. Crap. Shit. Sorry. I've got centimeters over centimeters to the -1. So hopefully we could see that that's the same thing as, dang it, centimeters squared. And notice that this whole thing is inside of a square root. So if I have the square root of centimeters squared, or if I have the square root of this whole guy, that means that overall this thing is going to have distance units. So the units make sense. It's a length. It's how far the neutrons diffuse before they get absorbed. That's a good fundamental definition to know, because like sometimes when people write the diffusion equation, they'll express it in terms of Bm squared, or maybe they'll express it in terms of L squared. If you know these kinds of fundamental definitions, you can look at the equation and not get scared if they rewrite it. Just know that they're just moving terms around. Um, and so if we know that lambda 1 is this quantity, and notice that this is bg squared minus bm squared, so we can rewrite our lambda eigenvalue like this. And that is going to help us with the time evolution problem. So going back to the time evolution problem, where we had this d by dt stuff equals negative lambda, we've identified what this lambda 1, our fundamental lambda, is, and we know that it's equal to this quantity right here. And we'll also just assume knowledge of some initial condition for this time evolution function. Notice that this differential equation right here, that looks just like the decay equation, differential equation. It looks just like the attenuation differential equation. The solution to this is going to look like some constant times an exponential. And then the negative lambda is going to be inside of the exponential. But because of the definition of lambda, I can rewrite this the lambda as v times d times bg minus bm squared. So we already said that the scalar flux, I've broken it up into these two functions. We found what the spatial shape function was. It was R1 of R. That was the shape function. And then the time part is this guy right here. It's T naught times the exponential of negative speed times diffusion coefficient times bg squared minus bm squared times the time. And all of this is inside of the exponential. And the only other thing I'm going to throw up front is a constant. And that constant is going to represent the the flux magnitude of our reactor. I didn't multiply by that constant at the beginning because the equation is homogeneous, which means that you can multiply through by any constant and it doesn't change your solutions. So we add this constant at the end that just reminds us that, that's going to give us our flux profile a maximum value or a magnitude. So this R1 of R, that's the shape function, and that's going to depend based on my geometry. Every kind of geometry, like a sphere or a cube or a cylinder, has its own fundamental mode shape function. And there is a corresponding value for this flux magnitude. And you can find that flux magnitude from multiple ways. I'm going to show you guys how to find it in a couple different ways, but it's always relating it to some aspect of the reactor, like its power or its reaction rate at some point. So this right here is like the solution to our original differential equation. And we can use it specifically, we can use this time part to better understand how this system is going to evolve with time. So when we talk about criticality, it is implying that we have a steady state condition, that our flux isn't changing with time, and we can use this equation to get some new criticality conditions. So notice that this part right here is going to influence my time behavior. And specifically, it's going to depend on, and notice that this is the same thing where I have a lambda 1 that can be written in terms of, I can write this in terms of lambda 1, or I can write it in terms of this whole thing right here. This is lambda 1. And so notice, if I look at the sign of lambda, that's going to determine if I have a configuration that is critical or supercritical or subcritical. And that's also going to be based on which is bigger, my bm squared or my bg squared. So notice that in terms of the sign of lambda 1 and the sign of this quantity right here, notice they both have a negative up front, so they follow the same trend. Like if lambda 1, so if we have bm squared greater than bg squared, that means that this quantity right here is negative, but that means that I have a negative times a negative, which means overall inside of the exponential, I have a positive number. So if bm1 is bigger than bg squared, bm squared bigger than bg squared, I am supercritical. And it also means that lambda 1 is going to follow the same sign as this. So if bm squared is bigger than bg squared, that means that this lambda 1 is negative. And if I have a negative times a negative, I get a positive in the exponential. If I have a positive exponential with time, that means my population is increasing exponentially with time, and that's what we call supercritical. Notice that if bg squared was equal to bm squared, then this whole thing in the exponential would be 0. I would have e to the 0, and that means no change with time. And that would also mean that if bm squared equals bg squared, that means lambda 1 is 0. So this means lambda 1 is 0, and this means that my reactor is critical. And then lastly, if bg squared is bigger than bm1 squared, that means lambda 1 is going to end up being positive, and that means that my configuration is going to be subcritical. There we go. So these are some new criticality conditions, and they help us understand that the criticality condition of a reactor, we can express it in terms of the balance between the material properties, the Bm squared, and the geometric properties of our reactor, the Bg squared. And when we're designing a reactor and we want it to be critical, we need Bm squared to be exactly Bg squared. We need to find a reactor that has the perfect match of its material properties and its geometric properties for us to hope to design a system that is critical. So we, just like we know K equals 1, K greater than 1, K less than 1, and those criticality conditions, we also need to know these criticality conditions. We need to be able to talk about criticality in terms of K, in terms of the BMs and the BGs, and also in terms of the lambdas. So hopefully that is pretty clear and that we could see how those are, how we how these conditions lead to those reactor states. I wanted to real quickly talk about this buckling term just so we have a bit more physical kind of understanding of what this buckling means. So this was our Helmholtz equation that we had for the space component. And if we get Bn squared by itself, it means we're gonna like subtract over the Laplacian, and then we're gonna divide both sides by Rn. So ultimately, if we have the Bn squared is gonna be 1 over R of R, Rn of R, times the Laplacian of R of, sorry, times the Laplacian of R of R. And that's R sub n. So remember that the Laplacian is like second derivatives. So this Bn squared, it looks like just some value, but then times a second derivative. And if I have the second derivative of a function, what does that tell me about the function itself? Like, when we look at the first derivative, it tells us about the slopes of our function. What does the second derivative tell us about? Curvature, or like the concavity of our function. So when we have our fundamental mode corresponds to Bn equals 1, so B1 squared is our Bg squared, and this geometric buckling, that's exactly what it represents. It represents a measure of how much our fundamental mode solution is curved or buckled, or it's like a measure of the concavity of our fundamental mode solution. So this is showing the first 3 eigenfunctions for a 1D slab. And notice that this function right here, that's the only one that's always positive, and that's the only one that can be our scalar flux function, right? Because this guy right here, he has negative values, and your scalar flux can never be negative. So we can automatically eliminate this as a possible eigenfunction, and we can eliminate this as a possible eigenfunction too, because it also has negative values. So generally, that's what Bg squared is. It's curvature of your solution. If you have an infinite medium, if that means that your dimensions are infinitely large, it means that your Bg squared is going to be 0. And that means you're going to have no solution curvature. You're going to have a flat profile. And there's going to be, just like there's a different shape function for every geometry, there's going to be a Bg squared for every geometry too. So that's just conceptually what we want to think about when we think about what the geometric buckling means. So now what I want us to do is solve this problem for a flux shape. And the shape that we're going to look at is a sphere. So we're going to imagine that we have a bare homogeneous sphere that has an extrapolated radius that we call capital R. And so we want to solve this one group diffusion equation in steady state to get the fundamental mode flux distribution. If it tells you that you're finding a fundamental mode flux distribution, what does that mean about my time derivatives? They're 0, right? Fundamental mode means we're looking for a critical configuration. We're looking at the system in steady state. So the time derivative goes away. So we're just looking at this one group diffusion equation. And if you take this equation and you rearrange it, you can get it into this form. All we're doing is getting the constants off of the Laplacian. So we're basically dividing both sides by negative d. We're moving everything to one side, and then we're factoring everything attached to these to these fluxes away. So if you can verify that this Bm squared matches the definition that we gave right here, that if you rearrange everything, this is your Bm squared. So this is our equation, and we want to fully specify what the problem is. So we need to talk about all of our related conditions. So the extrapolated boundary condition is going to say that our flux at the extrapolated radius, r tilde, if it's a bare sphere, that means it's surrounded by vacuum. So what's the flux have to be at our extrapolated radius? 0, right? That's our vacuum boundary condition. Physical realizability says that our flux function, the phi of R, has to be bounded. And what does the flux have to be bounded between for it to be physically realizable? 0, infinity, perfect. So it can be 0, but it cannot be infinity. So we include 0, but we do not include infinity. Do we have any initial conditions? If it's a steady state problem, there's no time dependence. That means that there's no initial conditions. So that's kind of a trick question. There's none. We are in steady state. So there's no time dependence. Therefore, we don't need to specify an initial condition, and we don't need to include time arguments in any of our functions. So those are our conditions. In our equation, we have the Laplacian of our flux. So for this geometry, we want to know what the Laplacian is. Does anybody at the top of their head know the Laplacian for a sphere? And if you don't, it's okay, it's in that table. It's going to look like 1 over r squared times d by dr of the quantity r squared times d phi dr. That's what the Laplacian looks like for a sphere. So if you think about the Laplacian for a 1D slab, it's just second derivative of your function with respect to the variable like x. This looks almost exactly like it, but we break it up into two derivatives. We put a 1 over r squared out here, and we put a r squared in here. That's, yeah, question? In this case, our function, it's a sphere, and it's a 1D sphere, so the only variable is little r. So in this case, we don't need partials because it's only one variable. But yeah, if you had like a cylinder where it has a height, so like a z component, and it has a radial component, then your partials, yeah. And if I go back to that table just real quick, just to see where we're pulling this from, this is the Laplacian for a sphere. Oh shit, no, that's for a cylinder. Sorry. This is for a sphere. But if it was for a cylinder, then notice that you've got a part that is radial dependent, and you've got a part that's axial dependent. And so here I do use partial derivatives, but here I don't. Good question, thank you. Oops, okay. This is an alternative boundary condition we can use. We don't have to use it, and actually we won't use it in this problem, but it's a good one to know because it can simplify other problems you'll see. For these flux, what we're going to see is that this homogeneous sphere has symmetry, that everything around it is the same, and the sphere is uniform. What that means is that the flux is going to be peaked in the center, and then it's going to decrease smoothly as you go radially outward. So what that means, because of the symmetry of the problem, it means that my flux is going to have a maximum in the center. And if the flux has a maximum in the center, it means that the derivative of my flux at r equals 0 has to be 0. This and when we look at the solution, I'll show you this just so we can like visually verify it. If you have a bare homogeneous reactor, it doesn't matter the shape. It doesn't matter if it's a brick or a sphere or a cylinder. The flux is always going to peak in the center of a bare reactor. So at the center, you can always say that the derivative of your flux has to be 0. So that's all of the conditions that we need to solve the problem. And once we write out all of the conditions, we can do math and we can get an answer. So all I've done here is I've rewritten the Laplacian, and I'm writing the shape function with a subscript n just to remind myself that there's many n's where this equation will be true. And all I've done here is I've rewritten my vacuum boundary condition in terms of my shape function. So when you get a differential equation like this, what we're going to see, and I'll talk more about this tomorrow, but any differential equation you see in this class is basically going to have a form where you can either integrate it by hand by doing like separating variables or integrating factors like we saw on homework 1, or it's going to be like this, where the equation has a known form that we can recognize, we can jump to that general solution, and then we can figure out what our constants are going to be. So an equation like this, the solution looks like a sum of sines and cosines, but there's a 1 over r in the solution. So our general solution is going to look like this. I don't need a hat. Phi of r is some c1 over r times sine of bn times r plus a c2 over r times a cosine of bn times r. I've got a good table for us next class that's going to show you for all of the common differential equations we'll see what the general solution is going to be. This is one of those. Um, and so once we can recognize that this is the general solution that satisfies our differential equation, we can start thinking about possible ways to simplify this. Basically, we can figure out if we can eliminate a constant based on our boundary conditions. So if over here, I've plotted cosine of x over x, and I've plotted sine of x over x. Notice that physical realizability means that, so this is r, and this is phi. So notice that at r equals 0, if cosine of x over x is a part of our solution, then what's going to happen as we approach r equals 0 with this function, the cosine function? It's blowing up to infinity, right? And our flux is physically realizable. It can't blow up to infinity. So because of this, the trend of the cosine part, and because of physical realizability, we can eliminate that entire cosine solution from our problem. We're going to just say that this whole thing is 0 because of physical realizability. And also notice that if the cosine part goes away, then our function, the solution to our equation, is going to look like this nice smooth function. Notice that this nice smooth function has the trends that we were talking about in terms of at r equals 0. Notice that at r equals 0, what's my slope here? 0, right? So this agrees with our alternative boundary or our alternative symmetry condition, which is that here d phi dr at r equals 0 is 0. And that's a good thing. It means that the solution that we think is the one that we're going to go with agrees with the symmetry conditions that we know should be there because of the physics of the problem. So this is our equation, and it has to satisfy this extrapolated boundary condition. So we can plug in that extrapolated boundary condition, and it says that the value of this function is going to be 0 when r is equal to the extrapolated r. So I've got C1. I'm just evaluating this at r equals big R. So here I've got dn times r tilde all over r tilde, right? Taking this equation, evaluating it at my vacuum boundary condition. So the left side is 0 because of the condition, and I'm evaluating the right side at capital R. Notice that this whole equation is equal to 0. So I can divide away the R, and I can divide away the C1. So my equation actually says that sine of Bn times big R is 0. If my sine function is equal to 0, let's draw just a quick unit circle. Notice that remember the sine is our y component on the unit circle. So at what values of pi is sine equal to 0? Any integers of pi, right? So 0 pi, 1 pi, 2 pi, 3 pi, any n pi is going to satisfy our it's going to satisfy this. So that means that Bn times r tilde has to be equal to some integer multiple of pi, right? Oh, shit. That inside argument has to be an integer multiple of pi for the whole thing to be equal to 0. And we also know that the BG that gives us our fundamental mode corresponds to n equals 1. So if we evaluate this equation at n equals 1, that's going to give us BG. So if we're just saying B1 is the definition of BG, and if I plug in n equals 1 here, then B1 is going to just be pi over big R, right? It's just going to be pi over R tilde. So for a sphere, BG squared is just the square of that. That means for a sphere, BG squared is pi over R tilde. Shit, I'll get some more room, sorry. Pi over R tilde squared. So if you have taken 304 already, you've probably seen that before. That's where it comes from. It comes from solving the eigen problem for a bare homogeneous sphere and applying our boundary conditions. So that's BG squared for a sphere. And if we were to have done this with a different geometry, we would have had a different resulting shape function, and we would have had a different BG squared. But this is how it looks for a sphere. So from there, this is our solution, and this the constant that was attached to this, we're just calling it C of phi. It's some constant up front that represents the magnitude or like the height of our flux shape. So this is a plot of this equation with just I've plugged in an arbitrary value for the constant and I've plugged in an arbitrary value for the radius. So notice at what value of r does the function have a maximum? R equals 0, right? It has a maximum at r equals 0. And for a sphere, r equals 0 is the geometric center. Our flux is peaked in the center. If our flux is peaked in the center, where does that mean that our fission, if I know the flux, how do I compute the fission rate density? Multiply by sigma f, right? So we can say fission rate density is the fission cross section times phi of r. So this fission rate density is going to depend on the location in the reactor, right? If we evaluate phi at r tilde, then phi is 0, so the fission rate density is also 0. But if we evaluate phi at r equals 0, where our flux is the maximum, that means that our fission rate density is also going to have a maximum there, right? So the fission rate density is also highest. It has a max at r equals 0. And if my fission density is the highest at r equals 0, that means that my temperature is also going to be highest at r equals 0. So in these bare critical reactors, r equals 0 is going to be where your flux is peaked. It's going to be where your fission rate density is peaked. Therefore, it's going to be where your power is peaked, and it's going to be where your temperature is peaked. So if it's a bare reactor, the hot spot is probably going to be in the center. So this is the solution for a sphere. And you can follow these same steps to do this and derive what the fundamental flux distribution is and what the BG squared is for any other simple geometry. On your homework too, I'm going to have you guys do it for a cylinder. It's a good exercise to know how to do it for a slab. like or a cube as well. If we can follow what we did here, you're going to basically go through almost the same steps. You're going to have a different Laplacian for each geometry, which is going to kind of change the differential equations that you're working with. But if you've followed through with this, it's very similar steps to do this for any other geometry. For all these other geometries, if you were to proceed the same way that we just did, this is going to be the result of your BG squareds and your fundamental flux shapes for every kind of geometry that I could ask you about. These are like the most simple geometries we can do. These are nice because we can mostly do them analytically, like with just pencil. And the only times that we really need a calculator is anytime you end up with a cylinder, whether it's infinite or a finite cylinder, you end up with this J0 thing, which is a Bessel function. Um, Anytime you have a problem on the homework with a Bessel function, use your calculator, use a computer. I won't expect us to do any integrating Bessel functions by hand. But all these other things like cosines and 1 over r sine, those are things that we can and should be comfortable with integrating by hand. And we'll be getting practice with that. Yes.
Will this be right on the same or?
I think it would be similar if I were to provide it, it would be a similar story with the divergence and gradient operators where like maybe I would give you this table. I would give you that table and then you would have to know which shapes and which bucklings correspond to which geometries. I think that's fair because then it doesn't require that you memorize everything, but you still have to know what's what. Um, So, oh yeah, and then this flux magnitude on the right, you can express the scalar flux for any of these reactors as the flux magnitude times the fundamental mode flux shape. All of these flux magnitudes are found from the reactor power. So I'm gonna, in the time we have left, I'm gonna show us how you can do that for the sphere. Since that was the problem that we've been taking so much time to understand, we can fully understand it with just a couple more things. So notice we had already talked about what the fission rate density formula is, but that's expressing it again. We also know how much energy is released per fission. Do y'all remember when we talked about that? What we said for the energy released per fission? Approximately? 200 MeV, right? About 200 MeV per fission. So notice the fission rate density is the number of fissions per unit volume and per unit time. If I want the energy released per fission, that's what EF is, the energy released per fission. And if I multiply the fission rate density by the energy per fission, then the fissions will cancel. And now I'll have a quantity that's telling me about the energy or the power corresponding to my reactor. So the power density, which is Q triple prime, it can also vary with position. And it is just EF, energy per fission, times sigma F times our flux. So let's make sure we understand the units here. What are the units of the scalar flux? Little quiz review. Neutrons per unit volume and per unit time. Do we need anything else? CM in the top, right? Because it's a path length, right? The centimeters up top is the path length part. It's a path length rate. That's why the time is in the bottom. And then it's a path length rate also per unit volume. So it's neutron path length per unit volume per unit time. What about the units for sigma F? What is the, yeah, 1/centimeters. And when we're talking about centimeters, it's what's going the distance. It's neutrons. So we can really think of this as number of reactions. We can almost think of this as the number of fissions the number of reactions. In this case, it's a fission cross-section, so it's fission reactions per unit neutron distance travel. So notice well, okay, and then EF, we said that that's MeV per fission. So I'm spelling out all the units so we can see what cancels. Notice that the neutron path lengths cancel. And also the fissions aren't a real unit, but I'm including them here just so we can see everything simplifies correctly. And so this expression has units of MeV per unit time and per unit volume. And MeV, what kind of unit is MeV? It's an energy, right? This is an energy, so it has MeV, shit. It's an energy. And so the base units of energy are joules. And so if we have energy per unit time, what kind of quantity is energy per unit time? Power, right? So the power is energy per unit time, and the units of power are watts, which is 1 joule per second. So if we have MeV per unit time, that's like a weird power unit. It's a weird power unit where if you multiplied by the conversion factor to go from MeVs to joules, then this would give you a power in watts. But right now, we can just say that it has units of power, and then it's power per unit what? Per unit volume, right? Because the centimeter cubes are still there. So power density, as we would hopefully expect, has units of power per unit volume. And if we have power per unit volume, what do we do with that expression to get just the total reactor power? You would multiply by volume, but what if my flux depends on position? You would integrate over the volume. Perfect. So this means that the reactor power, which is P sub F, is just the integral over the power producing region. So if you have like a multi-region system, you're not integrating over the whole reactor, you're just integrating over the part of the reactor that has fuel. So it's the volume of the core or the volume of the power producing region, and then we're just integrating the power density. So it's an integral of EF times a sigma F times a phi of R, and then we're integrating over the volume, so dV. And check it out. This phi of R, that's the fundamental mode flux. If it's a critical reactor, phi represents the fundamental mode flux. So an EF and sigma F, those are just like if it's a one region reactor, those are constants. They don't depend on position. So we can pull those out of the integral. And also, so we'll have an EF up front. We'll have a sigma F up front. And if I replace the flux with the flux magnitude times the shape function, the flux magnitude is also a constant, so it can also get pulled out. So I'll have a C of phi, and then I'm integrating over the core just my shape function, just R1 of R dV core. So that's like a fundamental definition for the reactor power. And hopefully we can see that if we have an understanding, or like even if we just memorize the fission rate density, you multiply by EF to give you a power density, and then you integrate that over the volume to give you the total power. And this is the governing equation that gives you those C phi values in the prior table. If you know what the power is and you carry this integral through, that'll give you a way to predict what that flux shape or flux magnitude is, knowing the reactor's power. So this equation, if you apply it to these various shape functions, it's going to give you these values of the flux magnitude. Ah, shit. I wrote flux. This is not for a 1D slab. This is for the sphere. As I was doing this, I changed my mind on which one I was going to do, and then I changed my mind back. So this is still for a sphere. I figured we should just carry on with the problem we've already been looking at. So all I'm doing here is writing the definition of power. It's this volume integral, but we can also write it like this if we pull out all of our constants and rewrite the flux in terms of the magnitude and the shape function. So I'm just integrating my shape function over the volume of my core. And what was the shape function for the sphere? That was the BG squared. This was the 1 over R times the sine of your um B. So this is going to be pi R over big R. So that's like sine of, yeah, B. The constant is the C of phi. So it's like when we here, the flux is the flux magnitude times the flux shape. So like going from here to here, I've substituted this in and then I've pulled the C phi out. So ultimately, we're just going to integrate this expression and then multiply by all these things together. And if we have a sphere, do y'all know how to write dv for a sphere? Do you want to know how to get the formula for that without memorizing it? Do y'all know, okay, we have to memorize something though. Do y'all know the volume of a sphere? Yes, perfect. So 4/3 pi r cubed. That's the volume of a sphere. That's something we have to memorize. I will not give you the formula for the volume of a sphere. The way that you get dv, ultimately, this integral depends on r. So we're trying to write dv in terms of a dr. And we can get that by taking the derivative of the volume with respect to r. So if I say dv dr equals, what's the derivative of this with respect to r? 4 pi r squared. Perfect. Do we all see how that's 4 pi r squared? Just doing power rule. This, you bring the power down so the threes cancel. You subtract the power by 1, so that becomes a 2. Cool. And then if I want to get dv by itself, I just multiply both sides by dr, right? So dv is just 4 pi r squared dr. It's always good to start with the basics. And if you can remember some basic thing and then do derivations from there, that's what I like to do. I like to do more understanding than memorizing if I can. But sometimes you just end up memorizing. I know how it is. So we can plug all of this into this definition right here. And so the constants up front are not going to change. I'm still going to have a C phi. I'm still going to have an EF. I'm still going to have a sigma F. I'm integrating over the volume. And now I've got 1 over R times sine of pi little r over big R. And then dv, right? My dv is 4 pi r squared dr. So notice this 4 pi can also come up front. What's going to happen with the r's? Can I simplify this at all? Yeah, the little r's. Yeah, perfect. Notice that we got 1 over r here, and we've got an r squared here. So ultimately, I'm going to have one factor of r in the numerator. So if you don't mind, we're just going to erase that and erase that. And if you, I'll also just erase the 4 pi and pull it up front. Hopefully that's okay. So this right here is what we've got to integrate. And if you do this integration, what you're going to end up with, keeping everything as it is here, what you should have is, so we've got the 4 pi up front, we've got the C phi up front, we've got the EF, we've got the sigma F. This whole integral, when you do it, should give you r tilde squared over pi. We have 1 minute left, so I don't have time to show you how to do this, but it's just an, if you were going to integrate that, what would be the technique? By parts, right? And do y'all know how to identify if it's integration by parts? It's if you're multiplying things, right? You've got a function times another function. At least that's how I think about it. If I see things being multiplied together, one of the things I'll try is integration by parts. So if you do integration by parts on this, this will be the result. And then if you get C phi by itself, that's how you get the value that's in the table. This is an aside. You'll need it for your homework. I'll talk more about it next time. So yeah, that is our class. Thank you all for your time. If y'all have any questions, feel free to let me know. Yes. Oh, for sure. If y'all have questions, let me know. If you need help with the homework, let me know. Don't forget the homework's due tonight at midnight. Canvas is set up, so you should be able to submit it there. And thank you for your time, and have a good rest of your day, and see y'all next time. Hey. Was it the beginning of class? There was. Unfortunately, I'm not gonna allow any like retakes. So 2 quizzes will get dropped. Just moving forward, make sure I understand like things will prevent us. Life comes at us fast sometimes, but just in general, if try to be here at the start of class. Yeah. Because if we have a quiz, it's gonna be, oh shit.
Will it always be at the beginning?
Yeah, they'll always be a theme.
All that slow motion.
I have a question about how to use Canvas.
I showed in that video too. Yeah, that's another thing. If you need help with Janice, I also went over that in the recording from Friday. Yes.
Canvas, on the back or?
You can keep it, but I won't be able to, I'm sorry. In the future, expect quiz first 5 or 10 minutes.
Yeah. Had a bad thing with my face, so. We'll just knock out. What's it with today?
Yeah.
Oh, that's weird.
Yeah, it'll be first 5, 10 minutes of class, and we'll drop 2, so listen, 1 will be okay. If you want to see what we went over, this was the quiz.
Just answers.
The answers are all in the notes, so like hopefully, yeah, it's basically just one of those homeworks. Yep.
There you said the punch. Okay.
Yeah, so that one is just an example. That's just like showing.
No, I'm just annoyed. I overslept by 5 hours on this, and it's just quantities and.
It's one of those, sometimes we got to take the L, but we also hopefully learn from it and we don't take the same L multiple times, right?
So, because I already on this last, my brother's wedding, and then, I can't draw on this, so it's already.
I didn't know, there was no quiz week 1. That's the first quiz.
Oh, I saw you posted,
I had posted it, but I decided not to give it on Thursday because technically this was the quiz I was gonna give, but I didn't talk about those 2 until day
that's
2.
what I noticed, so I was missing the check with the second lecture, and that's when I started finding out the reaction.
Yeah, so technically this was.
So, yeah, then I do have another question on that homework, but the questions, I wanna put this all out where, or, no, it's not.
If you, so this looks not, so if you wanted to just submit it like this. Yeah, that.
Put it on another sheet. Okay.
Yeah, like you're gonna end up scanning it into a PDF at some point, so when you do that, you could also like just add another page. That's how I do it. Yeah, because this is fine. I wouldn't waste time on unless you feel like you want to.
I just wanted to on because I thought I'll have on version, but it was mainly on the super question one. So I was the process not. Is it fine if I just did it?
Yeah.
Sure. The way it's fun. Yeah, that was great. Oh, I was in for the one question. I was just kind of confused on how you were asking about it. This is describe what particle. So was that in the process, or do we go down there and also include the time scale?
This is very similar to.
I know you have it on the left.
Yeah, that's what I was gonna say is that like the idea for that one is that it's almost like.
And that's what I noticed when I checked the lecture too. You had this about 3 steps as well.
Yeah, so like it's ultimately these are what I was asking for in terms of the time scales. This is what particles emerge, this is the time scales, and this is the energy associated with them. So it kind of looks like you've got most of this information there.
Yeah, because I even broke down.
Yeah, no, that's perfect.
Like that.
Yeah.
Okay.
You're good.
Hi,
Hello.
sir. I came in a little late today. My girlfriend called me because her dad went to ER and so like, all that stuff. So I didn't mean to miss class, but I came in like at 10:25 and I know I missed the first quiz.
This was the first quiz.
Yeah.
So yeah, technically if this was the one you missed, you've only missed one. Yeah, so I can't really make exceptions for anything that's not like a university excused
Yeah.
absence, because then I have to make exceptions for everybody. So, yeah, it's one of those things where like, I'm sorry that you missed it. If you want to see what was asked so that you can make sure that you're like understanding those questions,
Sure.
that would be good. Otherwise, I would say, try not to sweat it too much.
Okay, I remember you said that some of them were gonna be dropped.
Yeah, I'll drop two.
Okay.
Yeah.
Thank you, sir. I appreciate it.
You're welcome.
Mine's one of the ones, so.
Oh, okay. Sounds good.
And then-
Shimobi, is yours short too, or? Okay. Oh, yeah, what's up?
Out, look at on next Tuesday, so
Okay.
have a couple doctor appointments I need to make.
Okay. If it's a doctor's appointment, that should be university excused. Just, you would just have to go, like, I don't know exactly what that process is, but if you get it university excused and you show me that it's university excused, I allow you to make up the quiz.
So also just getting my ducks on the line, towards the end of this month, I'm planning on going on a 10-day trip. And part of it is gonna be looking at grad programs. Would that be eligible for some sort of remediation or?
I don't know. It would be based on whatever the university like policy is, I guess. The only thing I would say is that make sure the only thing that's going to be a real problem is if that happens during an exam. Because if you miss an exam and it's not excused, my hands are tied in terms of like letting you make that up. So I would say see if it's going to be excused. That would be like step number one. And then if it's not going to be excused and you're going to end up missing an exam, let me know that as soon as possible so that we can work out like taking the exam early, for example. Because that would basically be the way that I could do it, is that if you ended up not being here for the exam, I could give you an alternative one, like I guess it could be before or after. Let me know what they say about the excused absences and about the schedule, and then we can go from there.
Okay, and contact.
Do y'all? I don't actually know. Tamu. So this is basically defining what it constitutes a excused absence. So I guess I don't fully know the answer that if I don't know if you're supposed to send that to somebody or if it's a thing where like, one of the things is I'm sick, I'm in the hospital, and then I send, the papers to so let me double check, because I don't know exactly, like, it could be that you just need to like send me the doctor note and then that's fine. So I just need to double check, like I'm gonna go talk to Dr. Kimber and make sure I know how that's supposed to work out. Would you mind just sending me an email about this question so that I remember to reply, and I'll let you know what Dr. Kimber says in terms of how we could handle the absence if it happens during an exam.
Just send you an email.
Yes.
Okay. Sorry, last question I just remembered. I didn't really understand the bug plan. Like
Oh, okay.
physically, conceptually, you just said it was the curvature, but like the curvature of like this.
It's the curvature of the solution. So let's see. So lost. So yeah, these individual curves are the R. So the top one is R1. I believe the second one is R2, and then this is R3. And so the BN, it's just a measure of what the curvature is. And so, oh, actually, here, I can show you, maybe this will be a better way about it. Desmos graphing. So that fundamental mode flux shape, we have a phi that looks like 1 over x times sine of pi times x over big R. But that pi over big R, that's like the square root of our buckling, right? So if I write this as b times x, and then my bg is the square root of b, g, then, so notice that when right now I have b, actually, yeah. So as I make b larger, that's going to correspond to a larger reactor. Making b bigger is going to make the, shit. Okay, let me just write it like pi over r. That way, so I've got square root of pi. Sorry, I'm kind of doing this on the fly, but I think this will be useful for you. Sine of what is wrong? Oh, this is supposed to be. Sorry. Okay. Now this looks more like the form of our equation. So if we had a radius of 1, then our flux, it has like a very high amount of curvature. And if we made R bigger, what we're going to see is that the shape gets flatter. So when we talk about, notice that when I'm changing R, all I'm changing is BG. And if R is big, then BG is small, and then the curvature of my solution drops. And if my reactor dimensions get smaller, then my buckling or my curvature increases. So if you change BG, you're changing how much your solution shape is curved. Very, very large reactor, if BG was infinite, then if R was infinite, then BG would go to 0. And then you would have no buckling and you would have no curvature. Your profile would be perfectly flat.
Okay, so it's just how much the flux has changed.
How much the solution shape is curved. Yeah.
Just, well, that is.
This is just right. This equation is for a spherical reactor. So yeah, this is within the yeah, this would be valid from R equals 0 to R equals big R. So notice it is set up by definition so that this 0 right here is at your extrapolated radius. And if I make my extrapolated radius 2, then my function goes to 0 at 2, because we specified that boundary condition when we were solving.
That's what I want. In this one, you.
Right, yeah, when you're integrating over like the power producing region, you would only integrate over where there's fuel. Yes, hopefully that answers your question, right?
Well, so maybe just a compression of the word, like the definition of curvature.
Yeah, that's what the second derivative of function tells you. It's the concavity or the curvature, and a larger value of the second derivative just means more curved. And the sign of the derivative tells you if it's concave down or if it's concave up. But yeah.
Thank you.
You're welcome.
And I'm actually being
Thank you.
Okay, so
All right.
you have put that homework.
Yes.
Questions. Try to be as fast as I can. First of all, I understood that
Your homework looks really good, by the way.
thank you, I truly happy. So are we also including, so originally I just had n over centimeter squared times.
If you wrote n over centimeter squared seconds, I would count that. Because
Okay.
technically, you can cancel the one on the top and the one on the bottom.
Right.
And if you say it's neutrons per centimeter cube per second, then you're talking about a neutron density, which is not the same.
I don't know what I was thinking, or like, cause I know that it canceled, I think I was just, it was one of those days. Let's see,
We all have those days.
right, oh, mass, we're using the mass of the neutrons.
Mhm.
Okay, that was, something that I was trying to, sure, oh, so whenever I was calculating. Oh, let's get to this one first, this is, so I kind of got stuck when it came to,
Your answer to part A is right.
this one.
Oh,
Oh,
sorry.
sorry, this one,
Yes.
yes. Oh, yeah, that's what I figured. I think I was getting confused on how we're plugging that in.
Yeah,
Way-
I think I could have explained that better when we talked about it. So you've got n of t equals n naught e the negative lambda t.
Right,
And they are asking us about the half-life. The definition of half-life is the time for, can you finish the definition?
not off the top of my head, I apologize.
Time for the amount of the source to be had.
Yeah. Time for the amount to decrease to half or 50% of the original amount. That's what it means to have a half-life, is that when that time has passed, if you had 100 atoms, now you have 50.
Right.
So if so we're saying at t1/2, if I plug in this value of t1/2 into my equation, and I started with n naught atoms, how many atoms do I have at t equals
It
t1/2?
should be half.
Yeah,
of
It's
n naught.
n naught over 2. That's the value of my function at t1/2.
And so is that like considered the answer?
No.
That's what I was,
This
that's,
is what you
okay.
plug into here. So if I plug this definition into here, on the left side, I have n naught over 2. On the right side, I have n naught times e to the negative, what?
Wouldn't it be lambda t1/2?
Yeah, lambda times the t1/2. So this is what I solve for t1/2.
Oh, so are we just rearranging the equation to solve for t1/2?
Yeah.
See, that was, I wanted to make sure that that was
Yeah.
what,
That's it.
And that t half is equal to n naught over 2. You know, this program to make it into a t1/2.
And if I do that, I should get. So if you ever look up half-life, that's the formula they're gonna give you, and that's where it comes from.
okay.
No, it's just the opposite of the.
It's the reciprocal of the decay constant with ln of 2 and then. And yeah, the reciprocal, that actually means something too. If I write 1 over lambda, that means something else. That's the mean lifetime. That's t bar. So that represents the time on average this is the mean time. So this is telling you about how long it takes on average for one atom to decay.
Yeah, because that's lambda is still assuming that's the decay constant.
Yeah, exactly. Lambda has units of inverse time. So if you do 1 over that,
Yeah,
this quantity has
that's-
units of seconds. So it's the seconds it takes for approximately one atom to decay.
Okay.
Yeah.
Oh, so then know the decay constant actually on that whole time as well. Does that play into anything, or is it just?
Yeah, I mean, if you know the decay constant and you know how much of that thing you started with, this tells you how it evolves as time goes over.
Yes, sorry, I was meaning of the T-bar. Does that play any critical role in that equation? Or?
I mean, it's kind of like once you know this, you know that. And yeah, I guess I might not be understanding the question.
I was just asking if that plays any role into the end of T that we would kind of solve for that hat. Or is it just another type of value
Oh,
not
so-
even pertinent to that? It's all the same.
This comes from here.
Yes.
Yeah, so I mean, they're telling you about similar, this is kind of like, yeah, they're telling you slightly different things. This is a more like macro, like for the whole sample, how long does it take for half to go away? This is like if I was watching a specific atom and I wanted to approximate how, yeah.
So the ln of two, what happened? So I thought it was 1/2, and you make it ln, right?
You might have a negative ln of 1/2.
And so then that does the
It's-
recip,
yeah,
okay,
yeah,
okay,
yeah,
that
yeah,
makes
yeah,
sense.
yeah.
So sorry, I missed this one because it was, usually when I see it in writing things, then I ask the question. Here, magic numbers, I'm kind of getting a little confused, and the magic numbers and even and odd. I was looking, trying to search up, trying to go through all the material.
The place to go for that is, let's see if I go to our shared drive.
It was Lamarche.
Yeah, it's in March chapter 1. Mhm.
And yeah, so whenever I was looking through it, I just still couldn't comprehend it.
Oh, okay.
This is how to acknowledge, like how to write my answer in regards to the homework question. Because I also feel like I was getting really high energy.
Oh, maybe the numbers aren't matching. There's a calculation error. It could be meaning that it's messing up our conclusions.
Well, it's not just that, it's like
Oh, yeah, so there is some.
I figured there was something going on because it was like really high numbers. I mean, in the very beginning,
Oh, I see the
I
problem.
was getting, the pretty low numbers, but as I kept going, I kept getting pretty high numbers.
So. And this one. Okay, yeah, I think you might be making it harder for yourself. Because like, so for example, on this one, this is the reaction.
Right.
And the binding energy of that reaction is going to be based on the masses of these final products and the mass of the initial product. So what it looks like you're doing here is like breaking these guys up into their number of individual nucleons, right? At least that's kind of like what this looks like. Whereas
I
what we're
was using this equation.
right. So this is for the binding energy of the whole nucleus,
Okay,
not the binding energy to just remove one neutron. So so that binding energy equation, when we talk about binding energy, that like B, E, N, this is relating to the amount of energy required to assemble or disassemble the entire atom. So like if you were to take some nucleus and break it up into all of its individual protons and neutrons, what the energy, it's related to the energy difference between all of the individual particles and what they are when they came together. When you're talking about, so I guess that's really, I'm saying EE nuclear is that. EEN, which is the binding energy of the last neutron, is just the energy required to remove one neutron from that nucleus. So it's like if you started with A, X, Z, and you remove a neutron, you take one neutron out, and what's left is A minus 1. The same element, because the number of protons hasn't changed. So this is your governing reaction. And the binding energy of the last nucleon is just is based on the difference in the binding energy of these two, of this reaction.
so are you finding
You're looking up
each
the
one?
masses
Okay.
of the individual things. So like, what's the first reaction? It's for deuterium, right? So for deuterium, we've got 2H1 becomes 10N plus 1. Right?
Right.
So yeah, you would look up the individual, you would look up this mass, you would look up this mass, you would look up this mass, and then you would do the binding energy calculation based on those. So, Yes.
Wait,
Yes.
oh, are you doing, so the main one, so the first part minus the second, the mass 2 and mass 3? So
Um,
mass 1 minus 2 and 3?
Yeah, but binding energy is weird because the delta M, like in every other class, delta is always final minus initial. But when you write mass defect, it's initial minus final. It's weird.
Mass defect, but then I go back to the energy. That's where. Isn't it the product is minus?
Yeah, you can, it's always based on like, fundamentally, it's always based on what's on the left side and the right side of that reaction. And it just depends on what that reaction is telling you. So, yeah, like when we went through it in class, it was for disassembling and reassembling the whole atom. But if your reaction is telling you about just removing one neutron from the nucleus, then the binding energy calculation you're doing is saying, this is the binding energy associated with removing atoms
And are,
versus removing all of the atom, all of the particles from.
See, if this mass 1 would have the higher energy for us, it's mass 2 and 3. Or would it be mass 2? Well, no, it's separating, so it's, then this form would it be, became.
The mass, yeah, there's gonna be a difference in mass, for any nuclear reaction, and the binding energy is related to, how much energy gets released or required to make that reaction go, depending on what kind of reaction it is, and if it goes forward on its own, or if you have to like add energy to the reaction.
Well, that's what I was assuming is since it's on that equation right there, if it's removing a neutron. It was at a more excited state, and that's why it's separating to become less stabilized than my time. Or is that more just on the binding or not the mass?
So the binding energy curve is helpful to see, like, it's the binding energy per nucleon. So that curve tells you where nuclei are more tightly bound, and it tells you which way energetically, which reactions are favored. And it's any reaction that results in your products having more binding energy than what you like started with. Because so that's the case with fission and with fusion, that in both of them you're going up the binding energy curve, which means you're producing nuclei that are more stable, and that releases a lot of.
I was making sure, that's what I put down for question. On the long vision.
Yes, yeah, that's exactly right.
Give off it. It's a kind of opposite ends, or from your lecture slide. You go higher up on the number of CD.
Yeah, it's the
Base is on the mass.
it's the number of protons and neutrons. So yeah, A is just the protons plus neutrons.
so once you find the difference in mass, then you put it into like where it's mass times c squared.
Yeah, delta M times C
And then-
squared.
Well, if you just change n root to NEV over c squared, kind of against the c squared. And that's how you find the binding energy for, okay. And so when it comes to the, okay, at that point, when it comes to the magic numbers, you find all those answers, right?
So yeah, what you're gonna do, you're gonna do this for. Let's see, so yeah, like you're doing it for, this is a good example. When you do it for carbon 12 and carbon 13. So you're getting B, E, N for carbon 12, and you're getting B, E, N for carbon 13. What you're gonna find is that this one is much, much bigger than this one. And it has to do with the fact that carbon 12 is a doubly magic nucleus. It has 6 protons and it has 6 neutrons, so it has even numbers of protons and neutrons in the nucleus.
And so that's where it goes with the even, odd, even, or
Yeah.
odd, even, and then odd.
Just
odd,
based
whatever.
on which amounts of protons and neutrons you have. And the whole thing there, which I think is really interesting, is like the nucleus has a shell structure, just like the electron cloud has a shell structure. And so the electron cloud being filled in certain ways, the electrons tell you how atoms participate in chemical reactions. And if your electron cloud is full, then you don't want to exchange any electrons, so you don't react with anything, like our noble gases. The nucleus also has a, you can think of it as having like a shell-like structure, where if you get a filled nuclear shell, then the nucleus doesn't want to participate in any interactions that would change its nuclear structure. So it's not going to participate, or if it is participating in a nuclear reaction, it requires a lot more energy to change its nucleus. Because of the fact that
Right.
those magic numbers and it being a uniquely tightly bound nucleus. And any more explanation than that is like quantum mechanics. So that's as much as we really need to say about it.
Right,
Um,
so magic numbers don't just go for protons, they go for neutrons as well.
Yeah, and that's a funny thing because of the strong nuclear force being based on, it's like when you put a nucleus together, the protons and the neutrons act like a glue that keep everything together on the short range. Because if you had a nucleus that was just made of protons, all of those protons want to repel each other, and so the nucleus would just spontaneously disintegrate.
Okay.
But it's a funny thing with the strong nuclear force, where you suddenly add neutrons into that nucleus, and now the protons don't want to repel.
Right. Okay, so then there's the infinite uniform medium, when it's the one that we did in class.
Mhm.
But apparently it said that they added an extra step to it,
Yes.
which when I was looking back, they already had source in it that I was noticing. And first of all, I don't really know how to derive the source to find.
Okay.
It would make sense.
Yeah, here, let me actually just.
So I know if I find part A, I'm gonna be able to find part B, and I just want to figure out how overall that works.
So when we had an infinite. When we had an infinite medium problem, the way that we started is that we looked at all of our gains and our losses. So we were saying change rate equals gain rates minus loss rates. In this case, the quantities that we have to like kind of keep track of is n is the neutron density. V is the neutron speed. And then phi is the product of n and v. So all of these have units of neutrons per second. So the change rate equals the gain rates minus the loss rates. So the rate of change is about, this is the n, this is the population that we're monitoring. So the rate of change looks like a d by dt of n. N has units of neutrons per centimeter cubed. So if I just want the number of neutrons in a particular volume, I have to multiply by the volume.
Right.
And in this case, we can just multiply by the volume because it's an infinite medium. And so really what we're doing is we're multiplying by a subvolume in the infinite medium. And so that if we call that volume V, then that's what our rate of change term looks like.
Right.
And I can pull the V out, so I've got volume times dn dt. And that's going to equal all of my gain rates minus my loss rates. So in an infinite medium, what are my gain rates?
I believe there is it fission of it minus the absorption for loss rates, correct?
Yeah, and so if we had fission production, that could be one gain rate. So when we're breaking this down, we could say production, but we could also say sources.
Right.
So when we talk about production, that's like a fission reaction rate. Do you know what the production term looks like?
The weird,
New.
and then that'd be the macroscopic cross-section of fission. And then there was, I believe, one more term that I'm not, for whatever reason,
So the full term here would be the flux speed.
Yes,
But
yes.
also, if we want to write this in terms of the neutron density, then the flux is just n times v.
Okay,
So times n times the little v, or times the speed. And so this right here is neutrons per unit volume. V is centimeters per second. Sigma F is, we can say reactions per neutron distance traveled. And then nu F is neutrons per fission per reaction. So notice the reactions cancel. The neutron path length here cancels the neutron path length here. But this whole quantity right now has units of neutrons per unit volume per unit time,
so then you multiply by velocity again.
multiplied by the volume.
I
Right.
mean volume, yes.
Yep, and that's my centimeters cubed. That will make this cancel with that, so that this whole quantity, this production term, has units of neutrons per second. So that's the neutrons per second being produced by fission in a subvolume of our medium. The source was the other thing that they kind of are telling us about now, that this external source has units of neutrons per centimeter cubed. So if I say plus the source, and it has units of neutrons per centimeter cubed, then what do I need to hit that with to make my units match?
I feel like you need volume,
Yeah.
there's something else with time that you need to work with, right?
Right now, we're just setting up the differential equation. So all of these quantities have to have units of neutrons per second.
Right,
So-
well, that one doesn't have time in it, so that's why I was saying that.
Oh. Centimeters cubed per second.
Okay, okay.
Did I leave the units out of there? Because I thought, let me just double check, because if so, that's a big typo on my part.
You probably.
I I just want to make sure, because, yeah, no, because yes, okay, if you look in the, yeah, it's per, I just forgot the time when I was writing it there, because I'm going off my head. So yes, so all we have to do, right, is hit it with the volume, and then this. Those
And then,
cancel.
yeah.
So this is the neutrons per second being born from our fission source.
Right.
And then we have the loss rate term. What does that look like?
Which would be the macroscopic cross section of absorption. And which would be the, is it neutron density or, and then velocity, and then also times volume, so it can cancel out the
Perfect.
centimeters cubed, and then in
That's
the
the
end,
flux.
all of it would end up canceling all the volumes
The
out.
volume cancels every spot, right? And that's the last thing that we want to see. So you were asking, how do you derive the equation? That's how you do it. And all we're doing is adding in this one extra term, but the volume is going to cancel out when we divide it through on both sides. So then this equation right here, this resulting dn dt, that's what our overall differential equation is going to look like. And that's a differential equation that you can solve using an integrating factor.
Okay, so it also mentioned that, there would be an n naught in it, and so,
Mhm.
that was where I was thinking that we would have to derive the, due to time, so the dn over dt, you'll do the integration of that.
Uh-huh.
And I just couldn't figure out how you would do the integration with, source in it.
Yeah, so adding the source is what complicates the problem here.
Cause I got to this part, that was
Okay.
no issue for me, it was after
Gotcha.
this that I couldn't figure out where to go.
I see. So I'm gonna just rewrite this real
Of
quick.
course.
dn dt. This n and that n are the same. And that's ultimately, like, I'm trying to find a solution to n. N as a function of time is like the thing I'm trying to get out of this. So if I have my n here, then this n is being multiplied by e, by nu f, by sigma f. Then I have a minus sigma a. And so hopefully you can see I'm taking this over here. I'm
Right,
factoring out the n, and I'm kind of factoring out the v.
correct,
And then I have plus,
the source. 'Cause
So
I-
if the source wasn't here, if that was gone, if we just covered him up,
Right.
do we know how to solve the equation? Okay, the source complicates things because now the integral is not, it's not separable. You can't divide it so that you get one thing that's a function of n and another thing that's just a function of time. So you have to approach this in a slightly different way. And so I said, do it by integrating factors. That's kind of the wording to tell you the way that this looks like a differential equation of the form dy dt equals some function of y plus some constant. This is like a classic form of a differential equation, and the way that they will tell you to solve it is by this thing called integrating factors. I can show you a reference that I like to use to solve differential equations like this, because the integrating factor thing always kind of confused me, but you can turn it into almost a formula where you just look at this and you look at this and you ask the question, what's my function of y and what's my constant? And then you have some operations that you can do to build the
Right.
form of your
'Cause it just
solution.
looks like you'll just do source times, in this case, it'd be n, right? Or no, t would be source times t. Cause, okay, whenever you're integrating, you don't have, you can separate it by the integration of f of y plus the integration of c due to time, right? Do you mind if I run it?
Yeah, absolutely.
It's probably work.
Yeah, and if you want to take that space over
Yeah.
there.
So if I remember, because I just got finished, 309. This would be dy equals y of dt plus. Wouldn't this end up just becoming, f of, well,
Do we
Do
see,
do
do
you
we?
see where I'm going with though?
I see where you're going, but do you see any problem with how you've set this up?
Probably.
Oh, shit. And I also messed up because this is not f of y. Wait,
F
no,
of
this
t.
is f of y. That's the problem. That this right here is a function of, so in this case, n is the thing that we're solving for.
Right.
So here it actually is a, can I, because it is a y. And so the problem with what you've done is that this thing is a function of y, but you're trying to integrate it over time.
Right, okay.
And so that's why it's not separable, because you can't break it up so that everything that depends on y is on one side multiplied by dy, and everything's on the other side multiplying by the other differential operator.
Okay.
So yeah, so that's why it's of a different form, and that's what makes it a little tricky.
I never really understood the math of it, I just knew that it equaled that. And so for like at least 2 years, I'm like, yeah, that makes sense.
Everything is coming crashing down.
Okay. And like your reasoning, that's where it's like, oh, crap,
Yeah.
my memorization just.
That's why I try to not, if I can get away with memorizing, I'll do it. But if I can avoid memorizing, I like to do that as well. So we were talking about integrating factors. And there's a Paul online math notes. Yes. So section 2.1 of Paul's online notes, this is how I do this differential equation every time I have to do it. So they're writing it in a slightly different way that, so you've got P of t, which is, shit, and then I erased my, well, it's behind here. Our equation is in that form where y is n. This is everything that n was being multiplied by, right? Our v times that big, like, new f, sigma f minus sigma a
Yeah,
thing.
you're right.
And then g of t is the right-hand side. So like if I move the term that has n attached to it over here, then I have dn dt plus that constant times n equals my source term, right?
Right.
That's the form. And then this is how you integrate it. The way that you could start it is just like multiplying by this magic function mu, and then you do some stuff. And ultimately though, this is what the final solution, the final answer to your thing is going to be. You're going to take mu times that g with respect to time, plus the constant of integration all over this mu. And mu has a definition too, that mu is e to the integral of p dt. Yeah, so like that's it's basically just a knocking off the cobwebs on that solving differential equations using integrating factors. Nope. And I will give you a hint that if you go into Adam's notes, because ultimately you're going to get an answer there, but then you're going to be like, okay, but did I do it right? If you go to Adam's notes and you do Control F for extraneous, and you hit enter 2 times, right? That was our governing equation that we just wrote. We divided the volume to get this guy. If we do all the integrating, this is going to be our answer. So you will know that you got it right if you get this. Yeah. And notice, this right here is exactly what we got in class when there was no source, plus an extra source term. Yeah. So this is how this is the approach. You'll know that you got it right if you get this answer. Yep. Yeah, and then this is actually telling you the answer to the next part too, but you want to explain and show why this is the case. Don't just write this without explaining the math that gives you these numbers.
Right.
Yeah.
Okay, so now we're getting into. This is more of I did code, I coded something,
Cool.
and I don't know if that's allowed. I have written out code here. It was. So
Oh, is this for the mixture? Okay, yeah, that's fine. I don't care if you code for that. I did it in Excel.
I didn't feel like writing it all out and everything, but it says something about like your understanding how to do equations down. And I'm like, well, maybe I should check that out. Because, well, also, I don't know. Okay, first, this is my final answers, and I want to make sure that if they're too large, then I must have done enough out. Because
that's messed up.
right, no, that's fine.
It's cute,
That's
yeah.
why I didn't delete my code yet.
It's one of those things where, yeah, the orders of magnitude are about 26 times larger than what we would expect.
It's figuring, because I was like, I feel like it's wrong. Well, Avogadro's number was what I was thinking. That was first of all coming into play. The reason why this is so big is because Avogadro's number.
Yes. Oh, so all of those cross sections are given in barns? Did you convert from barns to centimeters squared?
Bars. The cross sections here. Oh my gosh.
So there's your
That's my
there's your
issue.
factor of e to the negative 24.
Easy fix on my code. I can
That's why it's nice to do it in code, right? Because then it's just you add in that conversion factor and hopefully it fixes everything.
The only thing that would be tedious is me writing out individually all of this. Because I typed individually, I was doing my output. The reason why this is so large, because I wrote out individually each output.
That's a good way to like test and make sure, like that's a debugging check. I like doing that.
I did that was to make sure that one is my code giving me the right numbers, but obviously you can tell that the reason my max profit absorption, scattering total was still coming out to these large numbers.
But if you multiply it by e to the negative 24, that's probably getting you. Let me just pull up the answers and make sure that that is going to fix it.
Other than that, I mean, I think that code's gonna be just fine. I just wanted to make sure that if my code was coming out that way, that,
Yeah.
I was doing it right or wrong, or I could submit it that way.
So can I see your final answer that you have for like those cross sections?
Maybe use one of the-
See, I was getting sigma s is 0.5 to 3, but that's an inverse centimeters. So the problem is that because the conversion factor from barns to centimeters squared is just 10 to the negative 24. So that would change this exponent, but it wouldn't change that number. Our numbers up front are slightly different.
Okay, maybe, so whenever I was, so it was a very smart.
Mhm.
So what it was doing, right? So this is my loop. I was putting in each of the individual ones. This is, this is Avogadro's number. This is the density. Then you'll have the equation. This is the base equation where,
I see. So that WI, are you throwing in the value from the table?
correct.
That's part of the problem.
Okay.
Because notice in this table, this WI, it is already a decimal. So
So I would
if
have
you
to be
divide
divided
by
by
100, you're dividing by an extra 100
Okay,
that
well,
you don't need.
that will also change.
That'll affect your number of, that'll affect your decimal place, but it won't
Right,
affect-
won't affect my actual number, so that would be something that I will fix there. Then the total is the A plus S, which I would get the microscopic of A and the microscopic S, and then they'll add it to T, and then each time that this loop ends, it adds it to the total of all of it, because isn't it the equations, you're adding all of them
It's
together
a
by the end
summation,
of it?
yeah, so that
Right.
should be fine. The only thing you would want to check is your like indexing, just to make sure that like, if you're going, just making sure that you're including every input. If
It
that makes
shouldn't
sense.
every input, because every time I input here, the ending of the loop should add it back into this.
Okay, yeah.
That's why, and it's from range of 0 to 10, which should include, I checked it like 5 times. but
Okay,
it
yeah,
gives every
that's fine,
single-
as long as you double check your outputs, because that's the only thing with coding is that, this one
Yeah.
is almost like, you could have you could have a bug in your code that would make it hard to find. But yeah, that makes sense.
Because it really could be that I just did something wrong, so. Let's say, drink. I've put in, I will start from the top and make my way down, and it matches everything. And so, like, this is the first one, right? This is the first line, this is the absorption, scattering, and the total of it. And I was here, but obviously the only thing that would change from this would be the decimal places.
Yeah, because you're gonna end up changing, well, the decimal places aren't gonna affect n. The decimal places are gonna affect your cross section.
Okay, so this
So you're
should be
gonna-
correct.
Yeah, the number
regardless.
density shouldn't oh, well, because of that factor of 100,
Okay.
it will affect that.
So, do you think the best idea to check why my number's off, not just the decimal places, but like the final answer, is go through the first one and do the math by hand, and then see where I'm doing that wrong?
Unfortunately, yeah, that's probably, it's one of those things where if you want to make sure that you're getting the right numbers, it makes sense to at least do some of the calculations by hand, just to make sure your code and your hand calcs are
course.
agreeing. Yeah.
It just helps that I know that my final answer, like actual numbers wrong, and
So I
check
can tell you that your total cross section should be about 0.54 inverse centimeters.
total cross section is what?
0.54
Centimeters?
inverse centimeters. Yeah.
Yeah, right, yeah.
Yeah, so that's the number to like look for, right? If you get that for your overall total cross section for the mixture, then your process is right. And then it also means your sigma A and your sigma S were right because they added up to give you that value.
I promise.
No, you're good.
One more question in regards to the graphs here. So these are the graphings that I ended up getting. It took me a hot minute because apparently saving it to my computer did not mean I could see the image, which I redo it like 2 times. So no, that's my fault. I've used this before. I should have known. This is the last one. My thing is, I'm probably not understanding the concept of how to explain it.
Okay.
Conceptually, like looking at the graphic and be like, oh yeah, well it increases there, and then it, has this big thing here,
That's
and
basically what I'm looking for.
people
Yeah.
it's just basically like, oh yeah, see that looks really pretty right here, but then all this mess comes right between these
Yeah, so like,
entities.
if we were explaining this, how would we describe it in the thermometer?
Words slowly. It's saying steady.
It's like constant, right?
Yeah, it's almost constant.
Relatively constant for low energy.
Like this one right here is like extremely constant here, and then shoots up after the fact, but we're only carrying from here to here, so it's just staying constant into a very, very slow increase.
Yeah, so some of them will be constant a little bit afterwards. And that's actually also kind of a trend, like that's almost constant. That one's a little weird, but most of them are also constant after the resonance region, at least for a
Yeah.
little bit. And then once you get into the high energy range, they all start floating up.
Okay, so I think when I was getting to, this is why fast reactors are typically favored for breeding.
Mhm.
I couldn't fully understand fast reactors, thermoreactors, and the concept of breeding from that end.
So, this plot is that eta was it's almost like you can almost look at it like K infinity. It's a new F, sigma F over a sigma A. So it's kind of representing like the number of neutrons produced per absorption event. So for us to have a reactor that's critical, we need 2 neutrons per absorption so that one new neutron can cause a fission and another neutron can just like get absorbed into something without. That's how we can make everything be steady and have one fission cause another fission and not have 1 cause 2, cause 4, cause 8.
Right.
So in our reactors, like large reactors everywhere in the United States, they're thermal reactors. So the fissions are mostly happening in this range where you're getting about 2 neutrons per fission neutrons per. So
Mhm.
to make a breeding reactor, you need more than 2 neutrons per fission so that 1 neutron causes a new fission, 1 neutron gets absorbed into something that like we don't care about. If you have 3 neutrons per fission, then that third neutron can go into, say, uranium-238. If uranium-238 captures a neutron, it can transmute and become plutonium-239, which is fissile. So if you get more than 2 neutrons per fission, if you get 3 neutrons per fission, you can make 1 cause a new fission, 1 get parasitically absorbed, and another one be absorbed into a part of your reactor that will produce a new fuel atom. So high energy means we get more neutrons per absorption. It means we have the potential for that third neutron to make a new fuel nucleus. So that's the breeding aspect of it. Uranium-238 can become plutonium-239 if it absorbs that third neutron. And though in that case, we're making new fissile fuel in our reactor continuously. And that's the idea behind. That's why breeding reactors are always fast. You'll never see somebody talking about a thermal.
Yeah.
If you hear somebody talking about a thermal breeding reactor, they're blowing smoke.
Like at the fast reactor, you have that higher energy, not have a higher probability to be absorbed in the thermal.
That's part of it too, yes.
But then that's why also like saying like China's fast reactor, what's it fast reactor?
They've done like
They've
everything.
done like the thorium one where they use the 238.
Yeah.
238 is more of a
Thorium does the same thing that,
breeding.
yeah, thorium-232 can become uranium-233, which is also a fissile nuclei.
Are they all fast? Well, that's another thing is I'm trying to understand like.
Fast is like energy above like around 1 MeV.
So this is 1 MeV
Mhm.
and it shoots up, that is considered fast.
Yeah,
'Cause
neutrons.
this is the part this is where I'm looking at.
That's the intermediate.
That's why I thought Compton and stuff. Right.
That's Compton is for photons.
Right.
That's where that's your resonance. That is where you get Doppler broadening and those sorts of.
But when we come to the fast reactions or fast reactors, we focus on whatever is after 1
Mhm.
and how this shoots up in it. But if it was, continued to be constant, it wasn't considered a fast reactor. Is that what you're saying?
No, the fast reactor is just about what's the energy, what is the energy of the like so our flux, our scalar flux has an energy distribution. In our thermal reactors, I'm running out of in a thermal reactor, neutrons, when they come out of fission, they're always born fast. So We talked about that chi of E as a function of E. That's the fission spectrum. And we saw that it looks like this. And it's peaked around 1 so this chi, it's a probability density function, and it tells you the likelihood, the y-axis, you can almost think of it as like a probability, or it's a probability density, that a neutron at a specific energy, the probability that a neutron coming out of fission is born with this energy. So from this spectrum, we can see that the most probable energy is about 1 MeV. So when neutrons come out of fission, they come out with, on average, 1 MeV of energy. That means neutrons are always born fast. And if we make a thermal reactor, a reactor that's designed to work on neutrons in this energy range, the neutrons were born over here, so we need some way to slow them down to that low energy range. And that's why we use neutron moderators. That's like water in a reactor or graphite in a reactor. And we'll talk more about this. We'll get more into energy dependence later. I think right now, all we need to know is that the thermal energy range is above 1 MeV. Sorry, the fast energy range is above 1 MeV. The thermal energy range is like about like 10 or so of an MeV. So like around, a tenth of an EV. So 10 to the negative 6 MeV would be 1 EV. 10 to the negative 7 would be about 0.1 EV. So 10 to the negative 7 is about our thermal energy range. Anything from 10 to the negative 7 below. So this is the thermal energy range. Thermal reactors are mostly, the fissions in a thermal reactor are mostly caused by neutrons in this energy.
Okay.
And if it's a fast reactor, then there's no moderator in a fast reactor. All the neutrons are born fast and there's nothing really slowing them down. So in a fast reactor, new fissions are caused by fast neutrons, and the fast neutrons are going to be in this.
Okay.
I hope so. If that doesn't answer your question, because I kind of feel like I started rambling and attempting to answer that. If it's a question about like anything more detailed about the energy dependence than that, I would say we're gonna get into it more later. So as long as that like basic stuff makes sense, then I think we're
Yeah,
okay.
so one thing that I'd say is that, I've talked to you about, the accommodations that I have.
Mhm.
Memory is one of the biggest things, which is why I have the audio.
Gotcha.
You can say something to me for like 5 minutes, and then after it, I'm going to just blank out, not remember it at all.
I got
It's an issue that I try to work with, so I usually try and record things as much as I possibly can.
For sure.
I'm probably gonna do more research and trying to understand it. In no ways of me not paying attention. in
No,
ways of
I
me
don't
not-
take it that way.
Okay, I just want to make sure because some people kind of do sometimes think that.
No, I don't. Yeah, I mostly just care about, the teaching, and so I hold myself to a high standard, and I try to make my explanations clear and understandable. So
You
if anything, no, if anything, it's just like if I'm explaining extra, it's just because like I'm trying to make sure
No,
that
perfect.
it's being conveyed.
That's perfectly.
That's the same thing.
Yeah.
Memory, but if I can fully understand the topic, then I can explain it, then I don't have to memorize it.
Yes. Yeah, and that's what I strive for too, like the whole saying about like if you can explain something to somebody who doesn't know the material, that's how you can prove to yourself that you really know it. So if you can explain it to your grandma or your, some elder or something like that, that's always like a good barometer for like, do I really understand this or do I just think that I understand it? Or can I just communicate this to other people who do understand it?
Well, that's why I like my freshman professors always told us the rubber duck. So that's what I do sometimes, or if I have some new, hey, does this sound right? That's when I'll pull up ChatGPT and like, hey, this is topic of this, like, does this make sense to you? Like, I
Yeah.
know it's AI or whatever it'll say, but
Yeah,
I just
sometimes
want
ChatGPT
it's sometimes better just to say it and then read what you said if it
Yeah.
makes sense.
The only thing I would say, yeah, with ChatGPT, I use it for that kind of stuff too. When you do a Google search, you are rewarded for brevity in the search. Like you want to put as minimal information in there With a chat GPT prompt, it's the exact opposite. You want to give it as much context as you can. So if you're asking a question like that, a good thing to add into the prompt is like, be critical of my explanation. Don't just say yes
Oh, yeah, no.
to it, because it will gaslight you and it'll be like, oh, you're so smart, you got this, that's exactly right, and it's all BS.
I'm like, I know that's wrong, why, like,
Yeah, it's been a struggle, so I try my hardest to like concept based, this is why I memorize more than. It's really
Fair.
funny, is that I do have a memory issue, but I memorize more than I comprehend it because memorizing comes easy
Gotcha.
than it does the comprehension of memorizing the comprehension of it.
Yeah.
And so this is why I'm so much struggling with the topic of fission and fusion, which is really funny because I want to get into reactor designing.
Yeah.
And at these two classes, 301 and 304, are basically reactor designing.
Yeah.
And so I'm like, struggling. It's okay.
It's gonna be fine.
I mean,
I think you're doing great in the class. I think in terms of, like in terms of participation and like doing all the things that as a student you're supposed to do, I think you're doing great.
thank you. All right, well, I'm gonna go ahead and cut some classes I had to do. I'll get
Oh, are you taking other stuff?
2 other classes.
Holy crap. Okay.
Yeah.
Well, yeah, that is yeah, that just is even more like yeah, it's not easy to take that many classes all at once. So I empathize with your situation.
Doing a heat transfer and engineering 216, which so far haven't been too bad, but for whatever
Heat
reason.
transfer's cool. Heat transfer's like fundamental applications of like conservation of energy. So in that sense, I kind of like statics because every problem starts with Newton's second law, and I kind of like heat transfer because like every problem starts with energy conservation. So it's like you have some guiding principle that's starting every problem. And here we're kind of doing the same thing. It's just conservation is the governing thing.
Right. Well, so situation happening right now is that they had one thing that has a unit of Kelvin, and then on the top it's a unit of Celsius, and for whatever reason they cancel out, and I don't understand.
Oh, so you know that if you convert from Celsius to Kelvin, it's 273.15 is the difference.
Right.
So if you're converting from a temperature value to another temperature value, you include that conversion factor. But if you're converting a delta temperature to a delta temperature, the delta is the same because you're subtracting the same 273 or adding the 273.15 in both places. And when they define thermal conductivity, it's defined as a delta T over a delta X. So the units are like, when you see a centimeter in there, or sorry, when you see a temperature in like your conductivity equation, even though you're reading the units as like watts per meter Kelvin, you should really read the units as watts per meter delta Kelvin. Because then the delta Kelvin and the delta Celsius have the exact same units because it's a delta, not because it's a single value. I didn't understand that until grad school. So yeah.
I'm sitting here watching, so I did the quizzes, I got like a 60, and I'm like, how? I thought I did it right. I gotta redo it again, and I got the same grade. And I'm like, but I redid it, and I even asked the professor all of my questions, and I'm like, is this correct? Is this correct? Is this correct? Yeah, everything's correct. Then what am I doing wrong?
Right. It was such a small thing that the professor didn't even realize that it was there. But yeah, that's the answer to why that's happening.
Okay, see, that makes me feel a little bit better, because I think I did get an email from him. But I'm not an online, it's all online. I did not do well in 2020 when COVID happened because
Yeah.
everything was online. And this is the only way I can take heat transfer was if it was online. So,
I see.
but anyways, thank you so much for your help.
You're welcome.
I'll see you on Thursday.
I will be here.
Perfect.
So,
No, he's good.
So for number 2 with the definitions,
Mhm.
the general, for scalar, I know it's, the scalar is equal to neutron density, neutron speed.
Mhm.
Do you prefer either, or do you usually more use this unit in class?
Technically, they're equivalent, but I will pretty much always write the scalar flux as a path length rate.
Okay.
per unit volume. And when I write J, I'll actually write the units like that. And that is partly what helps me, like they have technically the same units,
that's what
but
I
they have a
was-
different physical meaning. And so if I keep scalar flux like this, then when I hit scalar flux with a macro cross section, then the neutron path length cancels. And then I can use the scalar flux times a cross section to get a reaction rate density. Whereas this, it's already in per unit area units. So if I hit it with a dA,
Okay.
then it's giving me neutrons per second passing through that surface.
Yeah, that's what I was wondering, because yeah, I saw that in atoms.
Yep.
Net current or net current density or whatever
Mhm.
has the same units, but I was wondering more on the general expression. Is that what you prefer, or more on the lines of? Because that's what I was confused about on his atoms or Speckova's notes don't really give a, hey, here's the general, it's more blah, 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 blah. Here's a formula, blah, 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 here's a formula.
So I like these units for J, and then what you're basically saying is that it is a neutron crossing rate through a surface per unit time and per unit area. And really J, because J is the net current, it's about the net flow in minus out across that surface. So yeah, it's the neutrons per unit area, per unit time,
Yeah.
passing through some surface that's normal to the flow of the neutrons.
So would these be fine for the general expression, or? Cause you see, I did the 4 times, the 4 pi for the,
So there's a lot of different ways that you can write it depending on, so this and this are based and really,
yeah, more
The-
one's just a steady state, where this one's more real world.
yeah, this is like the more complicated way that you can express it. This includes the fact that J could depend on energy. So in this sense, this is just saying if you integrate J, the energy dependent J over all energies, you get back regular J.
Yeah,
I don't really think of the, so like, yeah, I don't necessarily think of it as any general, like, if I wouldn't ever ask you what's a general expression for J, I just
yeah.
ask you for a general definition for J, because that's part of what these are. It's like
Oh,
you're hitting J with different DEs or D omegas or whatever to think about.
I'm a very literal person, so
Yeah.
when you say give a general math expression, units and definition, I think for all. And that's why I was like, usually in the past, since when I took 3 or 4 last time, usually there isn't an expression, usually it's
I see.
the net current is part of another expression.
Yeah, so that's a good point. And that
Almost.
same, yeah. I see. So yeah, if I was gonna ask, if I forgot that I did ask about a general math expression. So what would I put for J? I think I would probably just put fixed law, actually.
And see, that's still,
I'm sorry.
that's usually the one we mainly use,
Yeah.
but then I'm like, we haven't really, because I missed Thursday last week. We didn't go over fixed law yet. So I was like, was he asking both general or?
We did
fixed
cover
law?
we did cover fixed law on Thursday.
I was,
Oh, okay.
that's what I was meaning, but I didn't see it
Okay,
in
got
the
it.
slides that you did.
Sorry. Yeah, I just misunderstood. I just wanted
Okay.
to make sure if yeah, that we knew that it was cut.
Okay, yeah, 'cause the last time I did it in 301, it was usually more fixed law, it was the only expression I actually did.
Yeah, I know. I understand your question now. Yeah, I think in terms of the net current, just using fixed law,
law.
because like in terms of any calculations that we do with a J, you'll either approximate it as fixed law or you'll have a net leakage expression that involves J. But yeah,
Okay. And for reaction rate density,
Mhm.
how do you prefer the units? I know we kind of did a little bit, but for reactions over the area times per time.
so if it's a density, it always, well, in that context, reaction rate density, it's actually telling you the units in the expression. Reactions per unit time makes it a reaction rate, and per unit volume makes it a density.
Okay,
Yeah, so it's reactions per unit volume per unit time.
so that's fine.
That's the units, yeah.
Okay, I was making sure I got the right units, and
Yeah.
then for the general, you prefer sigma
Yeah,
times?
Yeah,
or-
That is like that's what I, just like today in
That's what I
class.
prefer.
Yeah, me too. That's what I would be looking
Because I don't
for.
like writing
No.
that as the general for the whole volume.
No, and that is also, we've made a lot of assumptions that allow us to simplify
Yes.
the whole Maxwellian thing, and all of those assumptions
I-
allow us to, in fact, this definition only holds if we make those assumptions that we made about
Made.
the distribution being a Maxwellian,
To make-
all the nuclei vibrating isotropically, all that. Yeah.
That's what I was like. I said I'm very literal. So if
Mhm.
you say general, I'll need to find the general.
I gotcha.
But
Yeah,
I
that
know
makes sense.
Other times too, we don't use the general. It's more of the shortened general expression. And for micro and macro, of course, I did the spawns, and then I also gave
Mhm.
centimeters. But is that what you were looking for? Is the general expression? Because that's usually what we use
Yeah, that's
for
fine.
sigma.
Yeah.
And then of course, just the same thing
For
where it
mac-
was like over at reaction rate density. Now,
So this definition, it is kind of related to a probability, but it's like when you say how likely it is to have a hit and have a reaction, that is more like if you do a ratio of sigmas, like if I say sigma
well, that's what I was.
f over sigma t,
Yeah.
then that's the fraction or like the probability that if I have an interaction.
But since we're
it's
doing
a
total, what we want the probability, it's the total, so.
The definition should agree with the units. So if we say this is a quantity that has units of centimeters squared, our definition should say something that agrees with that. And so the definition I like is that it's the effective area that the nucleus is presenting to the neutron for whatever that reaction is. Almost in very simple ways, saying the nucleus is a sphere, and whatever that spherical area is that the neutron sees is the cross section. That's the physical meaning that I use for the micro cross section, because it makes sense with the units. But then we want to have the more detailed scientific understanding that like it's not really an area, but because of the units, it's very helpful conceptually to think about it.
Okay, so you just rewrite it a little bit, make it sound more confident and not a probability that it is actually crossing that area.
Yeah, it's more like a cross-sectional area than it is like a probability or a likelihood. It becomes a probability or a likelihood if you take ratios of little signals.
Yeah, I was just I didn't want to rewrite word for word what you put as definitions on the slide. I was trying to, but then
Yeah.
also with the macroscopic, would that be again, I need to change that from probability? Even though I know it's inverse centimeters, so it's per travel length.
Yeah, it is per unit distance traveled. It's more of the expected number of reactions. It's not a probability, it's the actual number of reactions. Per unit neutron distance travel.
Say we break those definitions. And then for mean free path, you prefer X bar or lambda?
I'll use X bar,
X bar, okay. That's what I was wondering too with,
and that was what I used on the quiz.
okay, that's sweet. And then, yeah, it was the centimeters. And then I just put average length that a neutron goes
Yep.
between collisions.
Perfect. Yep.
Okay. For Q, it's just the energy that we're correct. Because
Yeah, you
none of the
can-
books really actually say Q, they just say da da da.
Yeah, there's basically a definition in terms of the masses, and then there's a definition in terms of the final and initial kinetic
Yeah,
energy.
so I got the mass defect, where it was the mass of the, and then the products, reactants and the products times C squared. Is that the correct first?
Right, so
or-
that's the definition in terms of masses.
Mhm.
This is kind of like if you distribute the C squared n, that's giving you the binding energy definition, but from there, there's a kinetic energy definition too. So if I look up Q value, and I was looking at this on its nuclear Q value, not the statistics Q value. So two fundamental ways to write it, either a difference in the kinetic energies or the difference in the masses times C squared. So that was what I was looking for the two definitions.
So not binding, but kinetic.
Yes.
Okay, so I just need to. But then the mass defect, is that fine, or do I need to change it to?
No, the way that you wrote it there is is fine.
I just wrote the wrong, I needed kinetic rather than
Yeah.
bonding.
Mhm.
Okay.
Mhm.
Then for the Q value to be positive or minus for mathematically, I just did it as a decay where you have the parent decays with the daughter and the emitted particle. So then that has to give off more energy. Those have a positive, correct? Since the parent would have to have greater energy than the daughter and the particle emitted. Or am I having to have those crisscrossed?
I'm trying to think because the way that I answered this is using the kinetic energy definition. Because to me, that one is easier to say stuff about the things participating in the reaction. Because if it's final products kinetic energy minus initial products kinetic energy, you took Mariano's class. So imagine that this is a cobalt source. It's decaying. If we were to talk about an individual cobalt molecule in this crystal structure, and we wanted to talk about its initial kinetic energy before it decays, what would be a good approximation for the initial kinetic energy? It's like stuck in a crystal lattice.
For the actual amount of energy.
The kinetic energy of like that individual cobalt atom.
Um,
What's the kinetic energy of this object?
this object. Say zero, and this is just sitting.
Yeah, and even if we were to talk about an individual molecule vibrating in the lattice, it's not zero, it's more like K times T, where T is whatever the temperature is. But KT for something at room temperature is very small. So in terms of the initial kinetic energy, we can basically say zero. And then that cobalt radioactive decays. As it decays, it's emitting all of these different things that are moving in different directions. So how would we compare the final kinetic energy to the initial kinetic energy?
It would just be the final.
The final is basically all that there is because we're basically assuming
yeah.
that was zero at the beginning. So that's how I like to think about it because it's very easy to talk about it in terms of the
Makes
kinetic
sense.
energies. Whereas in terms of masses, you have to give me more explanation to justify why the difference in masses is going to be positive or negative. But it's a lot easier to explain it in terms of kinetic energies.
Well, that was the issue. I was trying to explain it because with the mass, that's what I was trying to do mathematically, because usually more of the time the parent will be saying this will have a greater mass than the emitted particles. And that's why I was trying to.
Yeah, and so you could justify it that way, but it's a more complicated explanation than talking about it in terms of kinetic energy, at least in my opinion. That was why I had to think about like, does that make like that does make sense, but it's just
Well, that's what I was about to ask too. So you want also a explanation? Because I thought we were just proving mathematically.
well, I think proving mathematically in this case is going to involve some kind of explanation in the sense that like if I do this explanation, I have to explain why
So
the
explain
initial kinetic energy is zero.
mathematically.
Yeah. I mean, because like in the solution process, you want to explain, like if I'm crossing out a term and saying it's zero, you can't just say it's zero without giving some kind of explanation for why. So similarly here, if you're saying the mass of A is bigger than these other masses, you have to then explain why the mass defect being positive means energy is being released. So you could explain that in terms of like the binding energy and things like that, but I think it makes conceptually more sense to explain in
the
terms of the
kinetic
kinetic
energy,
energy.
Because
definition.
it's zero.
Yep. So yeah, I see it's the thing again where the explanation is being taken literally.
Yes, and so you can see it's equivalent to something
I'm
else.
sorry.
So then, guess I just need to get kinetic energy equation for that, for the proof mathematically.
Mhm.
And then just explain it's sitting at a temperature, it's really good, assuming zero, because it's just staying still until it decays. Okay. And then,
And even if you assumed it had some value, the energy of the things coming out of that reaction is going to be so much greater than the vibrational kinetic energy that it's basically negligible. The initial amount is.
I know we talked about it a minute ago, like how fusion and fission both reduce energy. I just said both fusion and fission release energy because of the products are more tightly bound.
Mhm.
closer to the FE56 on the
Mhm.
binding energy curve.
Yep.
The gain in the stability shows as a positive Q value, which is the released energy.
Yeah.
That's
Yeah,
okay,
that sounds
one,
good.
that's good.
Yeah.
And then number one for the problems, I mainly just wanted to ask the questions, just because I didn't know how the formatting you wanted for
Yeah.
a ring response.
Yeah.
But I know the problems are more just show your work.
Mhm.
So for, then we got,
Yeah, that's right.
okay, sweet, so then. Oh, I'll send you the box. Then. So
Yeah,
that's
boxing
that.
any final
Yeah.
answers will make it easier for the grader, which is
So
probably
I
gonna
got
be.
for the
Yep,
total
that's right.
3.91.
Yeah.
Okay, sweet.
Yep. Thanks for moving. Sure. No, you're good.
Okay, cool. So like on Friday, so I've never got the Janus to work. I think
Oh, okay.
it's like open now. Okay, cause yeah,
Looks right. Go double click on the NEA, the bottom left.
this one,
Okay, and then we want incident and neutron data. So that
This one?
that one right there. And then that should give us all the libraries. So if we scroll down a couple, it'll give you the one I was asking for. Yeah, that one right there. And then we want cross sections. Cool. Okay, so then here you can select your nuclide. You could also scroll through it there. So like one of them is uranium 233. So let's scroll down to 92 for uranium. And then if we click on uranium, it'll show us his isotopes. And then if we click 233. Cool. Okay, so this down here is going to show all of the empty like folders for this nucleus.
yeah,
Um, so um,
21.
let's see. So 18 is for fission. We'll need him.
Did
And
I just
just real quick, if you open fission and then click that cross sections and click the check for P, then if you click P, it's going to give you a plot. If you unclick P and click T, it's going to give you a T.
okay?
So depending on how you want to deal with the data. But oh yeah, and this is just weird info about the, if you want to know the details of what went into these cross sections, that's what they're telling you here.
Oh.
But yeah, if we go back to the plot,
Okay.
So that's how you could find the plot of like a cross section of fission for any nuclide.
Okay.
Ultimately, what we want is that eta. So we need to make a function. And that means that if we go into tools and then computations, that's where we can take these individual MTs and make a function out of them. So if you click in the equation box here,
This. Okay.
then you're going to make the equation based on the individual MT files or folders. So it's like the eta, we're plotting eta, that's what, which is f sigma little sigma f over sigma. So the first things we want to multiply are nu f and sigma f. I think nu f is really far down. It's like 450 or something like that. Yeah, 452 nu bar total. So click him
Okay.
and then click the neutron production. I think double click. Okay,
Yeah.
so notice how that is like in parentheses. That is going to be multiplied by sigma f. So if you do a little multiply star,
This.
yep. And then we scroll up to sigma f, which was 18. Cross section. All right, and so now we need to divide by sigma a. So the division sign, they don't have sigma a by itself, but they have sigma f and they have sigma capture.
Okay.
And if we add those two together, that'll give us sigma a. Yeah, so open parentheses and then add sigma f plus sigma a. And I think if you scroll, oh, we're looking for sigma a. It's sigma gamma, which
Wait, what does it look like in the parentheses?
it looks like Z and then a comma and then the gamma symbol.
Okay.
I think it's a few more.
think you have it like in the electric.
Yeah, that was,
Is it
oh,
this?
there it is. Yeah, 102. So you have that guy.
And this is capture?
Yeah, they use the symbol gamma for capture. I use C just because more straightforward, I think. And then adding sigma out to that.
And that's just this, right?
Yeah, and if you scroll back up, it was MT18.
MT18, I got that.
Mhm. All right, and then close your parentheses. And then it's asking for a result name. You could call it Eta if you wanted, ETA.
And that is like this, right?
Yeah, that's the Greek symbol there.
Okay.
And then do apply and save. So it notice how like under these folders you have these individual things that you could click on, and it's saying under folder MT102 they are storing this calculation. So if you want to store it somewhere else you can, but if you see that is in 102,
MT102 is the capture per section.
yeah.
Right?
So if you press OK and then scroll down to the folder 102.
Okay. So right here is just the fission.
Yeah,
right?
that's still what you had
Okay.
plotted before. Mhm.
Okay. And then 102.
Now, if we open him up, we should see Eta down there. So now you can plot him, and that is now the plot of that whole quantity.
The whole thing here.
Yep. So you could take a screenshot of that. There's also, I think, a file. I think you can do file save. Yeah, however you want to. Oh, and just make sure you include the top, and make sure you include
Okay,
the.
so you want the whole thing.
Yes, sorry.
Okay.
Because the top will show you the nucleide as well, so that I'll be able to see
Oh,
that.
so you
and
want to
see
also
that
see
it's-
this and this.
Yeah, so
Okay.
mostly so I can see the oh no.
Okay.
Okay, yeah, back to normal. Yeah, so yeah, just include the title and include the axis.
Okay.
And you would just do, there's gonna be 5 plots. So
Okay.
that same process, but
Okay,
for
so
the
let me just run through the process just to make
Yeah.
sure what
totally.
so I can close this, right?
Yeah.
Okay. So how did we okay, well, let's start it. So
Mhm.
so initially I was doing this, I just it wasn't working, and then I did I should have done this something like that. So
And you're doing this all on the Mac too. I
Yeah.
have no idea how to.
yeah, I had to chat GPT, it wasn't working to me, like it just everything was going okay. And then I came over to the database, which is here,
Mhm.
and then the cross section,
Mhm.
which is here. And then we're looking at uranium, which is all the way down here, and then the isotope, right?
Mhm.
Which was 233.
Mhm.
Mistaken. Okay, and then I look for the cross section of the force. So the first thing we looked at was the fission.
Just real quick, would you mind scrolling down to 102 to
It should
see
still-
if that
it should-
102 was still saved?
I mean, I just want to be sure, like for the other ones.
Yeah,
trying to-
no, I just wanted to see because I haven't played around with this that
Okay.
much. I don't know if it saves over. Okay,
Okay,
so when you
it's
X
not-
out of it, it cleared it.
Okay.
So you want to make a whole new function, which
Whole new
means
function,
so we went
okay.
to tools at the top left,
So why did we open the fission one first?
just so I could show you how to plot.
Okay, cool. And then computation.
Mhm.
Right? And we're using this function,
Mhm.
which is signal fission, which is 18. All right.
Mhm.
Well,
That was the new bar, which
New
was
bar.
452.
bar is this.
That's this.
Oh, okay.
Because technically new is the neutrons per fission, but they could separate that up into the prompt and the delayed. For us, it's the new bar total.
Mhm.
So it's kind of like averaged and including prompting. Or prompt and delayed neutrons.
Okay.
Uh-oh.
Oh, okay. I have to like click out of it. Okay.
Yes. Yep.
That was like here.
Hmm.
102. Times the
Plus.
plus the
Yeah, close the parentheses. Open and close parentheses. Mhm.
And then apply and save.
Mhm.
That's right.
Mhm.
And then
Saving it in the same spot in that 102 folder.
I go down to 102 folder.
Mhm.
Uh,
And then you
Should
called
be
it
fine.
Ada. Yep,
and that's it.
that's it.
But I just take a picture of that.
Yep. Absolutely. And then you just repeat that for 4 more nucleides. But yeah, same steps.
Do you have a question regarding?
Yeah, that's what I said, was all of this, Janice on, over during the Friday help session?
Yeah, I mean, I walked through these same steps on the Friday help
Oh, so
session.
it's on the report.
Yeah, I just didn't understand it when you did it, so I just.
No, that was my other thing, is, are we just using Janice or can we use stable nucleides as well for the Tron and all that?
You're gonna end up needing, so Janus is where you'll find the cross sections, and that's where like all of these are coming from. The chart of the nucleides is more gonna give you like, well, I guess it depends on where you're pulling it from. If you're looking at some,
Yeah, sorry.
oh, I was just gonna say, as long as you can get what I'm asking for, I don't necessarily care where you do it. I was just showing how to do it from Janus because that's the one I'm most familiar with.
That's what I was just mainly wondering, because it does show you the vision and like the cross section of that as well. I just didn't know if Janice had maybe something, it was more structurally sound on its formatting.
Hmm. Um, in terms of the formatting, yeah, I guess I have a hard time comparing it against other things because I've literally only used Janus to get cross sections. So yeah, if you have another way of accessing that ENDF database, like I don't care where you access it from, but
I think he's more concerned in you
Oh.
getting the plot.
okay.
Right?
Yeah, that's what I
Right.
was mainly, or like, what was the first one question I was asking? I could try to see
Are you talking about question 7 or the other one?
either one that needs, but mainly the one with the plots.
I think that's question 7. Right?
Like 7.
Mhm.
Yeah, retrieve and plot.
Yeah, I think you
Yeah.
can only use Janus for that.
Oh,
I
yeah.
mean, that's
they
the only
use
people
that
we
at
use so
the end,
far.
yeah.
but Yeah.
File.
Yeah. Like, yeah, so I don't know where else you might be able to pull from those ENDF databases, but Janus is the place that I use.
Do you know how to use the web version? Because I feel like
No.
it's a bit more tedious.
It is. That's why I use like I could use the web version to get an individual plot, but then
Because you
once I
try
get an
doing it,
individual
like, it
plot,
doesn't-
I have no freaking idea like how to do stuff with that. So it seems like the downloadable version is way more user friendly,
Yeah.
especially for doing the computations, because I think with the web one, you would have to export each individual thing as a CSV, then plot it in like Excel, and then get all of those quantities and then multiply them together in Excel and then plot that. So
Oh, okay.
yeah,
Cause was it ENDF/B3?
Yeah.
That's the one, so we are doing the fishing process. I didn't want to see a table. See fishing cross section. For this is for UN 233.
Yeah, I think what he's saying is you're gonna have to want to be able to do this equation in whatever software you're using.
Oh.
And you can only really do that in Janus like with ease, except like you extract the data and then plot it like by itself in Excel or something.
that's exactly
And
right.
so it's gonna be more tedious.
It's going to be
versus
more
using,
work. Mhm.
Janus, and it just gives it to you
Okay.
straight up.
Then yeah, I'll just watch the help session video and see if I need to refresh on.
Sounds good.
Um. So like, what else can you use Janus for besides like index?
Basically any kind of nuclear data, you can extract it from Janus. So,
If I didn't want to use this, could I also use like that on Janus?
uh,
If I didn't want to like get the info.
oh, those kind of properties.
Do I
I
have to
bet
use
you
those?
can. Go back to Janus real quick, because it might be, because to get here, we did incident neutron data. I wonder if we go back up in the databases, if we go back up in the,
Okay.
oh yeah, so radioactive data.
Okay.
And then let's just check the same library. I bet that has like, okay, so what is decay, under decay, what does it give? I bet it's gonna give you that same plot. Let's see, check that top, that eye right there. Okay, yeah,
Okay, okay.
cool. Yeah, so that makes sense. It's gonna have all of that other stuff, and then it looked like there was decay data. There was also other nuclear properties. The decay path is probably cool because that'll show you like the decay kind of chain, I would imagine.
The interface looks pretty old though.
Oh yeah, this is probably like 80s or something.
Oh,
Yeah, and then
so
there's your decay
okay,
chain.
okay, so that's pretty cool. Okay.
Yeah, so like anytime you would need nuclear data, you could probably find it in JANS.
Because I've never really been able to get it to work.
Oh, gotcha.
And so, especially because like you barely find anything Mac on it, and then I
Yeah,
really have to go and check.
doing
None of the
engineering on
yeah,
Mac is just
none of the
extra hard
troubleshooting work,
mode.
yeah. So, but I got it to work.
Yeah.
Which is a good
That's
thing. Okay.
that's should be bonus points.
Yeah, and then also, I wanted to ask about like an excused absence for the exam.
Mhm.
I have to go to Nigeria for my brother's graduation.
Okay.
And so I was reading up on the thing you put up,
Yeah.
and so I think I just need to send you an email, like to formally notify you
Mhm.
that I'll be absent.
Mhm.
And then I can pull it up. Yeah.
Yeah, I mean, as long as it's falling under
Um,
an excused absence,
and
letting me
that-
know in advance.
It
and
basically just says that the absence verification, the instructor. The instructor may confirm a student's absent document,
Okay.
excuse an absence from attending class for the reasons stated in 7.2,
Okay.
or the reasons deemed appropriate by the student's instructor. So like
I
the
see.
7.2 doesn't specify graduation course. So like it's up to your discretion to if like
I see.
I can be excused for it, basically. So I don't know, is that okay?
Yeah, I think that should be fine.
And then the only thing I really need to do is just send you an email. Notification of absence. Most notify the instructor.
Okay.
For I think.
Yeah.
It's acceptable.
This will be okay. Just yeah, making sure that I get all of that in advance.
Okay, so what
and
exactly
letting
do
me-
you need in the email, and like when can I retake it? I should be able to retake it on the 24th or later. So from the set, so 24th of June or later. So it's a Tuesday, Thursday class. I'm just
Yeah.
thinking Tuesday or Thursday, so.
Right. I think what would be best is if you send me the email that's explaining what the absence is, and then explain what the dates are gonna be, and then
Okay.
from there, we can come up with a game plan that we both agree on in terms of when would you take the exam? Would it be before the trip or after the trip?
Okay, so in terms of like the dates, going to Nigeria is like a 24-hour trip.
Yeah.
On its own, like, so like I'm obviously like accounting for that and to meet the graduation itself. So like it might not include like the specific day of the graduation, but then I'm also accounting like for travel time and
I got you.
like the stress of actually making.
Yeah,
that
like if the graduation is on Wednesday, you still need all of Tuesday to get there and then all of Thursday to get back. At
I
the
would
very
need-
minimum,
Well,
that would
it's
be.
7 hours ahead, so I would need the day before, because if I leave on Tuesday, I
Just
won't
let me
get
know
it
that I understand it's
Okay.
gonna be just let me know what the window is, and then we
Okay.
can figure out what's gonna work in terms of
Okay.
doing it before the
So
window.
window in terms of the Tuesday, Thursday class time?
The window in terms of when you're gonna be gone.
Okay,
And I guess which days you're gonna miss.
okay.
That could be
I'm gonna be
helpful.
missed Tuesday and Thursday, so,
Yeah, just letting me know the window and then
Okay.
like I'm gonna miss this date and that date. That would be
Okay.
great.
okay. And then from there, we decided when I retake the exam.
Yeah.
Okay, cool. I'll send it to you like today, once I sit down.
Sounds good. Yeah,
Okay.
that's fine.
Thanks.
You're welcome.